Hi friends, welcome to our YouTube channel Knowledge Academy. The main of this lecture is to discuss the important formulas regarding the power electronics in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes on mobile. If any improvements you need in our lectures, then please comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. DC harmonic analysis. So this is a thing that we are going to learn in the starting. DC harmonic analysis. Suppose there is a voltage like this. It is going to have only the positive cycles. So definitely here for this signal, if you want to convert in terms of the Fourier series, any periodic signal we can write in terms of the sine and constant. So it is going to have some constant signal, and also here we are going to get some sinusoidal signals also, but their frequency are going to get changed. So this we are going to call it as the desirable. So this is what in DC harmonic analysis we need the constant value. So this is called as the desirable, whereas the sinusoidal terms are which are undesirable, because this is we don't need. This is what we don't need, but only this is the desirable in our DC harmonic analysis, whereas the sine terms are not desirable for the DC harmonic analysis. So we say this is the desirable quantity, whereas these are the undesirable quantities. So by using the Fourier analysis, I can convert this output voltage signal into the summation of the sine and cosine terms, which is A naught plus sigma n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. So this is the general format of any Fourier series expression. So finally here I can make the summation into some equivalent form, which is A naught plus sigma n is equal to 1 to infinity Cn sin of n omega naught t plus phi n. Means I can write the summation in terms of only one term, where Cn is the under root over an square plus bn square, whereas phi n is equal to tan inverse of an by bn. So it's a very simple way to convert this summation into a very one term. So therefore A naught plus sigma n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t, I can write, which is A naught plus sigma n is equal to 1 to infinity Cn sin of n of omega naught t plus phi n, where Cn is the under root over an square plus bn square, whereas phi n is equal to tan inverse of an by bn. So now here if I want to find what is the actual, or we can say what is the RMS value of this output voltage signal, so V naught RMS square is equal to, so we need to go for RMS of each and every quantity. So therefore we are going to get A naught square plus here. So for this expression we are going to find what is the value of the RMS, which is V naught RMS square is equal to A naught square plus 1 by 2 of C1 square plus C2 square up to C infinity square. So these are the terms that we are going to get. So by using the fundamental relation, so therefore V naught RMS square is equal to A naught square plus half of C1 square plus C2 square up to C infinity square by using the basic formula relation. So now I am going to take this. This is what we need. Desirable means the constant part we need only this quantity. So I am going to take it to the LHS, and I am going to take the under root over on the both sides. So therefore under root over V naught RMS square minus A naught square is equal to under root over half of C1 square plus C2 square up to C infinity square. So we want only these terms. We need only these terms, but these are the things which are undesirable. So we are going to get this is undesirable. So therefore we can say this is harmonic voltage. So these undesirable terms, if you are going to combine each and everything, so this is called as the harmonic voltage. So harmonic voltage is equal to under root over V naught RMS square minus A naught square is equal to under root over half of C1 square plus C2 square up to C infinity square. So these are the terms which are undesirable. So we are going to call this as the harmonic voltage. I am going to divide by the DC component, which is A naught on the both sides. Then I am going to get under root over V naught RMS square by A naught whole square minus 1. So this is what we are going to get after doing the division by A naught. So V naught H by A naught is equal to under root over V naught RMS by A naught whole square minus 1. So this we are going to call it as the ripple factor. So ripple factor is the ratio of the harmonic voltage by the DC component. So therefore, whereas form factor, see form factor I have already told you it is a ratio of the average value, or you can say form factor means I have already told you fra. So form factor means the ratio of RMS value by the average value. So RMS value is V naught RMS, whereas the average value is A naught. So therefore we can see the form factor is equal to V naught RMS by A naught. So therefore now we can see clearly this is called as the form factor. So this is called as the form factor. So ripple factor is equal to under root over form factor whole square minus 1. So this is a general expression. So therefore ripple factor is equal to under root over form factor whole square minus 1. So this V naught H is called as the harmonic voltage. So basically here what we have learned is harmonic voltage is equal to under root over V naught RMS square minus A naught square is equal to under root over half of C1 square plus C2 square up to C infinity square. So V naught harmonic voltage by A naught is equal to under root over V naught RMS by A naught whole square minus 1, whereas form factor is equal to RMS value by average value. So finally we are going to get ripple factor is equal to, so this ripple factor is equal to under root over form factor whole square minus 1. So this V naught H is called as the harmonic voltage present in the output voltage signal. If harmonics is present, then what is going to happen? If harmonics are present, means the sinusoidal terms are going to get present. So therefore definitely V harmonic or harmonic voltage will be equal. Means if these are absent, if harmonics are absent, means all the sinusoidal terms are absent. So therefore definitely we are going to get that harmonic voltage is equal to 0. Suppose this is the case, what is going to happen? Then, but I have already told you harmonic voltage is equal to under root over V naught RMS square minus A naught is equal to 0. So therefore if V naught harmonic is equal to 0, then we are going to get here V naught RMS is equal to A naught we are going to get. So therefore again, whereas form factor is equal to, see form factor is nothing but it is a ratio of the RMS value by the average value. If RMS value is equal to average value, then definitely form factor is equal to 1. Whereas ripple factor is equal to under root over form factor whole square minus 1. If form factor is equal to 1, then ripple factor we are going to get 0. So this is the desirable, means only if we get a DC component but not the AC components, then this is the thing that we are going to get, which is RMS value is equal to average value, form factor is equal to 1, whereas the ripple factor is equal to 0. So this is what we need, desirable. But if harmonics are going to present, then definitely the sinusoidal terms are going to present. So therefore the harmonic voltage is not at all equal to 0. Then what is going to happen is that V naught RMS is always greater than A naught because of extra terms are going to present. So V naught RMS is always greater than the V naught average. So therefore form factor is the ratio of the RMS value by average value. If RMS value is greater than average value, then definitely form factor is greater than 1. So ripple factor is equal to under root over form factor whole square minus 1. If form factor is greater than 1, definitely ripple factor is greater than 0. So therefore these are the undesirable things we are going to get if harmonics are present. So now we will discuss the AC harmonic analysis. Suppose there is a AC signal. It is also a periodic signal. So now here what I am going to do is basically, let me assume it's an output signal. So I am going to do by the help of Fourier series, I want to convert in terms of constant and also some of the sine terms or sinusoidal terms. So therefore you are going to get a DC signal plus some sine terms we are going to get. So you can see clearly in the AC harmonic analysis, the first frequency term is the desirable and remaining everything is are the undesirable. So therefore I can write in the terms of the sine and cosine terms by using the Fourier series. I am going to get V naught of t is equal to V naught plus Vm1 sin omega t plus Vm2 sin 2 omega t and goes on up to infinity. Whereas only the first frequency term, this is Vm1 sin omega t is the desirable and remaining every terms are the undesirable terms. So if you want to find what is the RMS value of the output signal, V naught RMS square is equal to V naught square plus half of Vm1 square plus Vm2 square up to the number of terms which are present. But here we need the first component. So this is the first RMS component. So therefore we can say that here V harmonic voltage is equal to under root over V naught RMS square minus V naught RMS of the first signal whole square. So V naught RMS of the first signal is Vm1 by root 2 whole square. So therefore this is called as the RMS value of the first component signal. Square is equal to under root over the remaining terms which are going to present are half of Vm2 square plus Vm3 square up to infinity terms plus V naught square. So therefore the remaining terms are the harmonic voltage. So this is the harmonic voltage. So harmonic voltage is equal to under root over V naught RMS square minus the RMS value of the first frequency term whole square. So therefore, if you take the division of V naught harmonic voltage by RMS value of the fundamental component, we are going to get under root over V naught RMS by V naught 1 whole square minus 1 is equal to THD. So this we are going to call it as the total harmonic distortion. It is the ratio of the harmonic voltage by the RMS value of the fundamental component. So therefore we can say THD is equal to under root over 1 by G whole square minus 1, where G is called as the ratio of the V naught 1 by V naught RMS, means your RMS value of the fundamental component by the RMS value of the total signal. So G is called as the ratio of the RMS value of the fundamental component by the RMS value of the total signal. So therefore THD is equal to under root over 1 by G whole square minus 1, where THD is the ratio of the harmonic voltage by the harmonic, or you can say here RMS value of the fundamental component, or simply we can say it is a ratio of the here RMS value of the harmonic voltage by here we are going to get RMS value of the fundamental component. See, if THD is equal to 0, then what is going to happen? If THD is equal to 0, then definitely the harmonic voltage is equal to 0, means no harmonics are going to present, then definitely we can say we are going to get only the desirable. So remaining all the undesirable are 0. Then definitely what we are going to get here, if harmonic is equal to 0, then definitely if THD is equal to 0, if you substitute here 0, we are going to get finally G is equal to 1. So therefore it means that the RMS value itself is equal to the fundamental component RMS. So both are going to get cancelled. So we are going to get ratio as 1. So output is a pure sine wave. But if THD is not equal to 0, then definitely the harmonic voltage is also not equal to 0, means harmonics are going to present, means so many number of frequency terms are also going to get present. Then definitely what is going to happen, the RMS of the overall signal is always greater than the RMS value of the fundamental signal. So therefore G is less than 1. So we can say as there are more number of harmonic signals, then definitely the output is not a pure sine wave, or simply we can say output is a distorted wave. So this is what we are going to get. So THD is equal to under root over 1 by G whole square minus 1, where G is the ratio of the RMS value of the fundamental component by the RMS value of the overall signal. Displacement power factor or fundamental power factor. So the displacement power factor or fundamental power factor means cos theta. It is the cos of angle between the fundamental output voltage and the fundamental output current. So therefore the fundamental power factor or displacement power factor is the cos of theta, means cos of angle between the fundamental voltage and the fundamental current. So cos of angle between the fundamental voltage and the fundamental current. This is called as the displacement power factor or the fundamental power factor. Where THD is called as the total harmonic distortion or harmonic factor. So you can call it as either total harmonic distortion or the harmonic factor, where G is called as the distortion factor. So G is called as the distortion factor. It's the value of G is going to lie between 0 to 1, because always G is the ratio of the RMS of fundamental by RMS of total. See, in the rare case they both can be equal or it will less than 1. So therefore G can lie between 0 to 1 only. So either it can be 0 or it can be 1. Only in this, between these two only it is going to get lie. So G is going to lie between 0 to 1, but it cannot be 0. So always from 0 to 1 only it is going to get lie. So therefore THD is called as the total harmonic distortion or harmonic factor, whereas G is called as distortion factor. So now we are going to learn about the characteristics of the switch. See here, ideal switch. So for ideal switch, now we will discuss the characteristics. So let me assume this is the ideal switch. So this is the voltage across the switch and this is the current across the switch. See, when the switch is on, definitely V is equal to 0. V is equal to 0 and current can be either positive or negative. So therefore V is equal to 0 and current can be any value, either plus 1 or plus minus 1. It can lie between any range. From minus -50 to plus +50 it can lie at any point. But P is the product of the voltage and current. So as V is equal to 0, so definitely power is equal to 0. If switch is off, means current is always 0, then voltage can be either positive or negative. So it can be at any value. So from -50 to plus +50 it can block any voltage. So power is the product of voltage and current. As current is equal to 0, so power is also 0. So therefore For ideal switch, when the switch is on, voltage is equal to 0 and current can lie between from -7 to +70. Always the power consumed by the switch is always 0. When the switch is off, then definitely current is equal to 0. The voltage can be either positive or negative. It can block any value of voltage, and always the power is nothing but 0. For a practical switch, what is going to happen? But for a practical switch, when the switch is on, there is a small amount of voltage drop. So voltage drop is ideally not equal to 0. It will be a small value. So V on is the voltage across the switch at the on position is not equal to 0. So but here current cannot lie from -7 to +70. It is going to have certain limits. So therefore the current in that wire, in that switch, can lie from some minimum value to maximum value. So it is going to have certain limits. And the power is the product of this voltage and current. So now if you do the product of these two things, it is not equal to 0. Therefore P is not equal to 0. But when switch is off, ideally the current should be equal to 0. But now even the switch is off, a small amount of leakage current is going to pass. So we are going to say that the current in the off position is not at all equal to 0. Whereas ideally it can block any value of voltage from positive to negative. But practically it can block some range of value, only some range of voltages from minimum voltage to the maximum voltage. So if the product of these two things, power, still you are going to get it not equal to 0. Means a small amount of power is going to get consumed. So we can say that for practical switch, when the switch is on, a small amount of voltage drop is going to get occur, and also current is going to have some limits from minimum to maximum only it can pass. And also if the product of these two things, the power is not at all equal to 0, means it is going to consume a small amount of power. Similarly, in the off position, the current is not at all equal to 0, means it will be a small amount of current is still going to get passed. And also it can limit only some minimum value to the maximum value of the voltage. So because of this, a small amount of power consumption is going to occur by the switch, practical switch. So now we are going to draw the characteristics of the ideal switch and the practical switch. So you can see clearly for ideal switch, when the switch is on, current is not equal to 0. If the switch is on, definitely voltage is equal to 0. Voltage drop because the switch is equal to 0, whereas current to the switch is not equal to 0. So if the product of these two things, power is equal to 0. When the switch is off, current is equal to 0, but the voltage across the switch is not equal to 0. So if the product of these two things, still power is equal to 0. So same curve is going to repeat again. So therefore you can see that the power consumed by the ideal switch is 0. But if you come to the practical switch, here current at on position, current is not equal to 0, but a small amount of voltage drop is going to get occur across the switch. So because of these two, product of these two things, a small amount of power consumption is going to get occur. Suppose in the off position, current cannot change instantaneously, so it is going to change in a small amount of manner like this. It is going to decay like this. So because of this decay, the switch is going to come to off position. So in the off position also a small amount of leakage current is going to pass. So therefore there is a voltage drop. So voltage drop is going to get increased. So you can see clearly this is called as a switching off condition. Means when you are going to switching off, the current is going to decay and the voltage is going to get increased. So therefore you can say at the off position both are non-zero, so the product is also not equal to 0. But during the switching conditions, this is at the steady state, but during the switching conditions also, if you do the product of these two things, you are going to get in this manner. So therefore you can see clearly again it is going to get repeat. So this is switching on condition and this is the switching off condition. It means you are going to switch off and here you are going to switch on. So this is called as the T off and this is T on. So therefore when you are going to switching on, the current is going to get increased and the voltage drop is going to get decreased. While switching off, the current is going to decay, whereas the voltage drop across it is going to get increased. So we can see clearly here this is called as the characteristics of a practical switch. So these are the characteristics of a practical switch and these are the characteristics of an ideal switch. So now we are going to do some certain analysis. So for these graphs, so let me assume current is equal to is going from 0. So it is going to means during the switching on condition the current is going to increase whereas the voltage is going to get decay. So finally it is going to come steady state and the voltage drop will be small amount of voltage drop. Even the switch is on, there will be a small amount of voltage drop for a practical switch. Again if you are going to switch off, the current is going to decay but the voltage drop is going to get increase. So this is the graph you are going to get. This is the on condition and this is the off condition, means switching on condition and the switching off condition. So let me assume this is the time Tc. So this is the time between these two instances is the Tc. So now we can see clearly then overall time. So this is called as the overall time. I am going to assume. See, overall time is the summation of the T on plus Tc plus T off. So now conduction loss. Conduction loss means during this steady state we are going to find what is the amount of power loss. So power is equal to product of voltage and current. So average power is equal to 1 by Tc integration of 0 to Tc Vi V of t into I of t dt. So in this time period I am going to find what is the amount of power loss in the conduction period. The conduction period is only in this time period. So 1 by Tc integration of 0 to Tc V of t into I of t dt. See, in the conduction loss both are constant values. So therefore this is V on and this is I. So if you do the product of these two things, finally see these two are constant values, you can take it outside the integration. So finally Tc cancels, we are going to get average power loss in the conduction period is nothing but V on into I. As switching loss. So switching loss is nothing but during the transient state, during the on period and during the off period, how much amount of power loss it is going to happen, we are going to see. So during the on time, the current is going to get increased, but the voltage is going to get decay. So we can simply say that the current is going to get increased. So I of t is equal to the slope of this is nothing but I by t on into t. So this is the equation of the current, which is slope of this into time t. So I of t is equal to slope I by t on into t, like y is equal to mx. So therefore, whereas V of t is equal to the voltage is going to get decay. So voltage is going to decay from V to 0. Let me assume from V to 0, it is going to decay in a time period of t on. So therefore, we are going to get V into 1 minus t by t on. So whenever the voltage is going to decay from capital V to 0 in the time period of t on, we are going to get V into 1 minus t by t on. Let I assume that V on is nothing but 0. So therefore now here, what is the power loss? The power loss is the product of the voltage and the current. So power is equal to V of t into I of t. You are going to get Vi by t on into 1 minus t square by t minus t square by t on. So you are going to get this one. So I want to know what is the energy, means what is the amount of energy loss in the on period. So energy is equal to integration of 0 to t on P of t into dt. So if you do these things, energy is equal to integration of power into time during this time period 0 to t on. So if you do this one, we are going to get Vi by 6 into t on. So this much amount of energy is lost in the on period. During the switching on condition, this much amount of energy is lost by the practical switch condition. So during the off time, we can say that the current is going to decay. So current is going to decay from capital I to 0 in a time period of t off. So therefore, the expression I of t is equal to I into 1 minus t by t off. See, whereas the voltage is going to increase from 0 to capital V in a time period of t off. So we can say V of t is equal to V by t off into t. I am going to assume the voltage drop in the on time is 0. So now we can see clearly power is the product of the voltage and current. So we are going to get this one. But I want to know how much amount of energy loss in the off period, which is integration of 0 to t of P of t into dt. So finally you are going to get Vi by 6 into t off. So this much amount of energy is going to last in the period of t off. Then finally I want to know how much of energy is going to last in the switching period, in the on condition and also in the off condition. So overall energy loss in the switching condition is equal to energy loss in the on period plus energy loss in the off period. So if you take the sum of these two things, we are going to get Vi by 6 into t on plus t off. This much amount of energy is going to loss in the switching condition. So now PS is equal to E by T. So this we are going to call it as the switching power loss. So switching power loss is equal to E by T. So PS is called as the switching power loss and T is the time period of one cycle and E is called as the switching energy loss. So switching power loss is equal to overall switching energy loss by time period of one cycle. So PS is called as the switching power loss, E is called as the switching energy loss, whereas T is called as the time period of one cycle. So now we are going to learn the classification of switch. So we are going to do some classification of switches on the basis of controlling. On the basis of controlling, we are going to get uncontrolled switch and the semi-controlled switch. So here you can see the first case, which is uncontrolled switch. Uncontrolled switch means the on and off state of switch depends on the circuit itself. See, the on and off state of the switch depends on the circuit itself. Means a person doesn't have any control on the on and off of a switch. that is purely depending on the circuit condition itself. So the on and off state of the switch depends on the circuit itself is called as the uncontrolled switch. Means a person cannot control the on and off state of a switch. Only the circuit is going to control the on and off condition of a switch. Example is diode. So therefore we can say uncontrolled switch means the on and off state of the switch depends on the circuit itself. Example is diode. Whereas semi-controlled switch means only one state of switch can be controlled by the user. Example SCR. Semi-controlled switch means only one state, either on or either off. Only one of them we can control, a person can control, and the remaining thing is going to control by the circuit itself. So that we are going to call it as a semi-controlled switch. Only one state of the switch can be controlled by the user, and the remaining state is going to control by the circuit itself. That we are going to call it as a semi-controlled switch. The example is SCR. Only the on condition of the SCR we can control, but not the off condition. Off condition is totally dependent on the circuit itself. Next one is the fully controlled switch. See, the both switching states can be controlled by the user. So fully controlled switch means with the help of this switch we can control both the on state and also off state of that switch by the user itself. That is called as a fully controlled switch. So both the switching states can be controlled by the user, then we are going to call it as the fully controlled switch. The examples are the GTO, gate turn off thyristor, transistors which are the BJT, MOSFET and the IGBT, and also triac. So these are the devices which are fully controlled devices. GTO, transistors like the BJT, MOSFET and also IGBT and the triacs. So these are the fully controlled switch. So on the basis of controlling we have learned three things: uncontrolled switch, semi-controlled switch and the fully controlled switch. Uncontrolled switch means the switching conditions, or you can say the on and off state of the switch is totally depends on the circuit itself. Whereas semi-controlled switch means only one state of the switch can be controlled by the user, whereas the remaining condition of the switch can be controlled by the circuit itself. Whereas fully controlled switch means the both switching states can be controlled by the user only, that we are going to call it as a fully controlled switch. Some of the examples of uncontrolled switch are the diode, and some of the examples of semi-controlled switch are the SCR, and some of the examples of fully controlled switch are the GTO, transistors like BJT, MOSFET and IGBT, and also the one more thing is triac. On the basis of blocking. So now we are going to see on the basis of blocking, we are going to see the classification of switches. See, unipolar switch. See, unipolar switch means which can block only one polarity of voltage. Example, diode. See, unipolar switch means it can only block only one polarity of voltage. That we are going to call it as a unipolar switch. Means diode. If you can see clearly, diode can only block the reverse voltage but not the forward voltage. So we can say this is a unipolar device. It can only block the only one polarity of voltage it can block. So it is called as the unipolar switch. The example is diode. Bipolar switch, which can block both polarity of voltage. If any switch which can block both polarity of voltage, then we are going to call it as the bipolar switch. Bipolar switch means yes, a switch can block both polarity of voltage, then it is called as a bipolar switch. The examples are the SCR, GTO and triac. SCRs, GTO and triac, all these three can block the both polarities of the voltage. That is the reason these are said to be a bipolar switch. So on the basis of blocking, we have learned unipolar switch, bipolar switch. Unipolar switch means only one polarity of voltage it can block, and bipolar switch means yes, both the polarity of the voltage the switch can block. So on the basis of current flow, we are going to classify the switches. Unidirectional switch. Unidirectional switch means the current is going to flow in that switch only in the one direction. Means the current can flow only in the one direction. That is called as the unidirectional switch. Means the current can flow only in the one direction in that switch. It's called as the unidirectional switch. Examples are the diode, SCR, GTO and transistors. So in these devices, the current flow is always unidirectional. Whereas in bidirectional switch, yes, the current can flow in the both the directions. That is called as the bidirectional switch. And some of the examples are the triac. So basically what we have learned is we have classified the switch into on different types. On the basis of controlling, we have classified like uncontrolled switch, semi-controlled switch and the fully controlled switch. On the basis of blocking, we have classified the switches like unipolar switch and the bipolar switch. On the basis of current flow, we have classified the switches like unidirectional switch and the bidirectional switch. So now we'll discuss some important points regarding the transistors. See, transistors, the first one is the BJT. So this is the symbol of a BJT. This is the base, collector and emitter. So this is the incoming base current, this is the collector current and this is the emitter current. So by using the KCL, emitter current is the summation of the base current and the collector current. So BJT means bipolar junction transistor. It is used for low frequency application. So always BJT we are going to use only for the low frequency applications, and it is a current control device. See, by using the base, with the help of base only, we are going to control the on and off of the switch. So we can say it is basically a current control switch. It is a current control switch. When IB is equal to 0, it is off. When IB is equal to 0, the switch is open. When IB increases, it is on. So we can see you can control both the on and off state. So it is a fully controlled device. It is basically a fully controlled because we can control both the on and off state of the switch. So it is called as the fully controlled switch. So therefore you can see it is a current control device. Based on the current only we are going to control the on and off of the switch. So because of this nature only we are going to call it as the current control device. And it is a bipolar device, means here the conduction is because of both the volts and the electrons. So that is the reason we are going to call it as the bipolar device, means both the volts and electrons are responsible for the flow of current. So we can say it is a bipolar device. So now we will discuss the MOSFET. So this is a symbol of a MOSFET. This is the gate, drain and source. So this is a symbol of a MOSFET. The expansion of MOSFET means metal oxide semiconductor field effect transistor. So MOSFET means metal oxide semiconductor field effect transistor. It is used for high frequency application. See, MOSFET we are going to use it for high frequency applications only. We are going to use for high frequency applications. It is a voltage control device. Means based on the gate to source voltage only we are going to control the and off state of the switch. So it is called as the voltage control device, and it is basically a fully controlled device. See, if VGS is equal to 0, the switch is off. Otherwise, if VGS is greater than the threshold voltage, then the switch is on. So therefore, we can control both the off and on state of the switch based on the gate to source voltage. So it is called as a voltage control device, and it is a fully controlled switch. So, but it is a unipolar device. Only majority carriers. There are no minority carriers. There are no minority carriers in this MOSFET. Only majority carriers are responsible for the current to flow. So because of this reason only, as the time period is very less, so therefore the frequency is very high. Means we can use for high frequency applications because it is a majority carrier device. So now we will discuss the IGBT. See, IGBT, the full form of IGBT is insulated gate bipolar transistor. Means it is a combination of both BJT and also MOSFET. So IGBT is a combination of BJT and also MOSFET. So it is called as a insulated gate bipolar transistor. So you can see clearly this is a gate, this is a collector and this is the emitter. So gate, collector and emitter. So these two are going to come from the BJT, but this comes from the MOSFET. So therefore you can say this is gate, collector and emitter, because it is a combination of both BJT and also MOSFET. So here it is a mixture of both BJT and also MOSFET, and it is also a voltage control device. If gate to emitter voltage, if it is 0, then the switch is off. If VGE increases, then it is on. So therefore the on and off state of the switch is depend on the gate to emitter voltage. So therefore you can say it is a fully controlled device, and it is good. The on and off state of the device is controlled only on the voltage. So it is called as a voltage control device. And here it is used for medium frequency application. So it is used for the medium range of frequency applications because it is as a bipolar device. Because it is also a bipolar device, means both the majority carriers and the minority carriers are responsible for the flow of current. So it is called as a bipolar device, like volts and electrons. So because of this, as the minority carriers are present, so it is used for the medium frequency applications, whereas BJT is used for the low frequency applications and IGBT is used for the medium frequency applications, whereas the MOSFET is used for the higher frequency applications. So now we are going to study about the switches and each and everything regarding the switches. We are going to see. The first one is the diode. So the diode symbol is here. This is the diode symbol. So with an arrow like this. So this is called as the anode and this is called as the cathode. So the direction of the current is in this manner, and this is the voltage across the diode. So So this is the voltage and this is the current. So you can see clearly the diode, the characteristics of the diode is it is a unidirectional. It is always unidirectional, means current only travels from anode to cathode. See, current can only travels from current is only travels from anode to cathode, but the current in the reverse direction is always equal to 0. So it is a unidirectional switch. Only current can travel only in one direction, and the remaining direction the current is 0. Uncontrolled switch means both the on and also off of the switch is controlled by the circuit itself, but not by the user. So it is called as an uncontrolled switch. And also it is a unipolar switch. It can only block the reverse voltage, but not the forward voltage. So because of this, it is called as the unidirectional switch, uncontrolled switch, and also unipolar. Suppose if you give a positive voltage, across this diode, the voltage will become ideally 0 and the current is a non-zero value. So you are going to get in this shape. But if you give a negative voltage, then definitely current is 0. So current is 0 means you are going to get like this. So therefore this is called as the characteristics of an or IV characteristics of a diode. So now SCR. The symbol of SCR is in this manner. Like this we are going to get a shape. So this is anode, cathode, extra one gate we need to keep for a diode. So you are going to get like this, anode, cathode and gate. So this is the current direction I and this is the voltage V. So it is also unidirectional switch, means only current can only travel from anode to cathode, but the current in the reverse direction is always equal to 0. And it is a semi-controlled switch, means only the on state of this switch is controlled by the user, but not the off state. So because of this reason only we are going to call it as the semi-controlled switch. And bipolar switch means here it can block both the positive polarity and also negative polarity. So because of this reason only it is called as the bipolar switch. So it is a unidirectional switch, semi-controlled switch and also bipolar. So if you try to keep a positive voltage, if you give a positive voltage up to a forward blocking voltage, the current is 0. So but the voltage is not equal to 0. But when the positive voltage is greater than the forward blocking voltage, here the voltage drop will become 0 ideally and the current will be non-zero. So these two things we are going to get. But if you keep a negative voltage, the current will be always 0, but it can block that voltage. So because of that we are going to get this one. So these are the IV characteristics of an SCR. So now a GTO. So GTO means extra symbol is just you have to keep a dash here. So if you keep extra dash for this SCR, you are going to get a GTO. Same anode, cathode, plus minus V, I current, and this is the gate G. So the GTO is called as the gate turn of thyristor. So this is also unidirectional, means current can only flow from anode to cathode, but in the reverse direction the current is 0. And it is a fully controlled, means we can control both the on state and also off state of this switch. Bipolar, it can also block both the positive polarity and also negative polarity. So because of this only we are going to call it as the bipolar switch. So GTO is basically a unidirectional switch, fully controlled switch and also bipolar. So if you want to know what is the IV characteristics, so if you give a positive voltage which is lesser than the forward blocking voltage, then the current is 0 but the voltage is not equal to 0. But if you give a voltage which is greater than the forward blocking voltage, then the voltage will be ideally is equal to 0 and the current will be non-zero. But if you give a negative voltage, that the current will be always 0, but you are going to this graph. So this you can see from this graph clearly that it is a unidirectional, because current can only flow in the positive way and it can block both the positive polarity and also negative polarity. So it is called as a bipolar switch and it is a fully controlled. So we can see from the graphs also we can tell about, so you can see clearly from here, see it can only block one polarity of voltage, so it is a unipolar, whereas this is only in one direction the current can flow, so it is a unidirectional switch. Whereas this one you can see clearly it can block both the positive polarity and also negative polarity, so it is a bipolar. Whereas here the current is only in one direction, so it is a unidirectional current. So whereas here you can see it can block both the voltages, so it is a bipolar switch, but here current can only pass through one way, so therefore it is a unidirectional. See now track. So track is nothing but it is a combination of two anti-parallel. So it's a combination of two anti-parallel SCRs. We are going to call it as the track. So therefore this is called as the main terminal 1 and the main terminal 2, because we don't know actually where is anode and where is cathode. So because of this only we are going to call it as the main terminal 1 and main terminal 2, and this is the gate. So this is the current I and this is the voltage V. So this is basically a bidirectional switch. In both ways the current can pass. Whereas fully controlled, yes, the on and off of this we can control with the help of this gate. So on and off is also being controlled with the help of this gate. And it is a bipolar, means it can block both the positive voltage and the negative polarity voltage. So it is called as the bipolar. So we are going to get a graph IV characteristics here. See, if you give a voltage, if you give a voltage which is less than forward blocking voltage, the current is 0, but the voltage will be non-zero. But if you give voltage which is greater than the forward blocking voltage, here the voltage will become 0 and the current will be non-zero. But if you give a negative voltage, suppose if you give a negative voltage up to certain reverse voltage, it will be current will be equal to 0. But after that the current is going to get pass. So therefore we can say this is called as the triad. See, you can see clearly it can block both polarity of voltage and current can flow in the both directions. So it is a bidirectional, or you can say it's a bipolar and also bidirectional, and it is a fully controlled. On and off state of the switch can be controlled by the user itself. Whereas transistors, I have already told you, the transistors are the fully controlled devices. So this is a BJT, base collector emitter. So this is a current type flowing from collector to emitter, and V is the voltage drop across the collector to emitter. Similarly for MOSFET, so this is a gate, drain and source. So this is the voltage across the drain and source, and the current is flowing from drain to source. And this is called as IGBT. So gate, collector and emitter. So therefore you can see clearly it's a combination of both MOSFET and also BJT. So this is a plus or minus V and is the current I. So this is called as the IGBT, this is called as the MOSFET, and this is a BJT. So therefore now you can see clearly always the current is only in one directional. So it is a unidirectional device. Current can only flow from either collector to emitter or drain to source. So it is a unidirectional, and in the reverse direction the current is always equal to 0. And fully controlled means on and off state of the switch can be controlled. It is a current control device, and these both are the voltage control device. So both the on state and the off state are controlled by the user. So it is called as a fully controlled device, and it is basically unipolar, means it can block only one polarity of voltage. So therefore we can say it can only block one polarity of voltage. So it is called as a unipolar. Suppose if you give a forward voltage, so if you give a forward voltage, here you can see if you give a forward voltage, then definitely it can block for small amount of time. Then after that, if it is greater than some threshold value, we are going to get the current. So we can say this is called as the IV characteristics of a transistor, whether it is a BJT, MOSFET or IGBT. So this is the thing that we are going to do. So it can block only the positive polarity. It can block only the positive polarity if the current is in the positive direction. So this is the IV characteristics of a transistor. So when the voltage is lesser than the forward blocking voltage, the voltage is non-zero but the current is 0. After that the current is going to have some non-zero. So it is only unidirectional. Current can only flow from up to down but not from down to up. And also it can't block, the reverse voltage also. It can't block the reverse voltage, and also the reverse current is also is equal to 0. So now we will discuss about the power transistors. These are the normal transistors, but now we are going to see the power transistors in detail. So here this is some switch. This is called as a MOSFET, power MOSFET, and this is the power IGBT. So these are the normal MOSFET and normal IGBT, but these are the power MOSFETs and the power IGBT. So power MOSFET means the extra, there is the internal diode. See here, for this there is the external internal diode from source to drain. There is an internal diode. Similarly, in the IGBT also there is an internal diode from emitter to collector. Internal diode, these are present inbuilt itself. So therefore now we can say that here, because now current can flow in the both directions, because in the reverse way this diode is going to, internal diode is going to help for conduction current to flow. So therefore this is called as a bidirectional switch, and it is also a fully controlled switch, and it is a unipolar. Means only it can block one type of polarity but not the reverse one. So that is the reason it is called as a bidirectional, fully controlled and unipolar. So now here when the current is lesser than positive forward blocking voltage, the current is non-zero, but it is a voltage will be non-zero, but the current is zero. But if it is greater than forward blocking voltage, the current will be non-zero, but the voltage is zero. But if you give a negative voltage, what is going to happen? This diode is going to get conduct. So internal diode is going to get conduct, and we are going to get a voltage of zero, but a current of non-zero. So therefore we can say it can only block a positive polarity, but not the reverse polarity. So therefore, because it is in the reverse polarity, it is going to get conduct. So here both the ways the current is going to pass, only it can block a unipolar. So therefore it is called as a unipolar and bidirectional, and it is a fully controlled switch. See, except diode. See, diode is a uncontrolled, and SCR is a semi-controlled, and remaining everything are the fully controlled. See, remaining everything is a fully controlled. Diode is we have learned in this fashion. The first one is the diode, SCR, GTO. Next one is a triac, transistors, and the power transistors. So diode is an uncontrolled switch, SCR is a semi-controlled switch, and remaining everything are the fully directional or fully controlled switches. Remaining everything is a fully controlled switch. So if you remember this one, see, this is like this shape. Add an extra thing, you are going to get like this. Same copy here also. So now add an extra thing here and cut these two things, we are going to get this one. Add an extra thing here, we are going to get like this. The easy way to remember is, if you know this one, add an extra quantity like this, we are going to get same copy paste here, and now add an extra thing for this one, we are going to get this one. This one we are going to get, and cut these two terms, we are going to get these branches, and add an extra thing here, we are going to get this one. So that is easy way to remember. So we can say that diode is a unipolar and unidirectional and uncontrolled switch, and whereas SCR is a bipolar, unidirectional and semi-controlled switch, whereas GTO is a bipolar, unidirectional, fully controlled switch, whereas triac is a bipolar, bidirectional, fully controlled switch, whereas transistor is a unipolar, unidirectional, full control switch, whereas power transistors are the unipolar, bidirectional, fully controlled switch. So now we will discuss regarding the devices. See, the devices regarding the GTO. The first one is the GTO. Now we are going to study. I have already told you GTO means gate turn off thyristor. Means it is basically a fully controlled switch. Means we can on and also we can off the switch. So this is a symbol. I have already told you this symbol. I have already told you anode, cathode, like this. So gate. We can write in another fashion also, like two arrows. Two arrows, or like this also you can draw. See, now see, these three are going to represent the same figure. You can, some textbooks they are going to give the symbols like this also, but generally these three symbols are same for GTO. Either you keep dash, or either you keep two arrows, or either you can keep like two arrows in this separate way also you can go. So any of these symbols are going to represent the same thing, which is called as the GTO. So now here plus Ig, if you give a positive gate current, then we are going to on this device. But if you give a negative gate current, means we are going to off the device. Means by giving a positive gate current, we are going to on the device, and by giving a negative gate current, we are going to off the device. Both IL and IH are very high in GTO compared to ordinary SCR. See here, both the latching current and also holding current are very high in gate turn off thyristor compared to ordinary SCR. So this is the difference between the main difference between the normal SCR and the GTO here is, here for this it has a large value of the latching current and also the large value of the holding current when compared to ordinary SCR. GTO is used in high frequencies compared to ordinary SCR, so it is used in chopper and also inverters. So GTO can be used in high frequency applications, whereas the SCR we can use it in normal frequency applications only. So GTO can be used in very high frequency applications when compared to normal SCR. So because of this reason only we are going to use the GTO as a switch in chopper and also inverters, because there we need a high frequency switches. So because of that reason only we are going to prefer the GTO rather than an SCR. It need high Ig to turn on GTO compared to ordinary SCR. I have already told you, because the latching current and the holding currents are very high, so it needs a very high value of currents in order to on the device and also off the device. So this is the difference between a GTO and also normal SCR. And also I already told you it's a high frequency applications when compared to normal SCR. So because of that only it is going to use in the choppers or the inverters. Now we'll discuss the RCT. RCT is called as the reverse conducting thyristor. So reverse conducting thyristor means here there is a thyristor but anti-parallel we are going to keep a diode. So this is called as the reverse conducting thyristor. So now if you draw the IV characteristics for the positive, suppose this is plus minus V and this is the current I, then we can say that. So for this voltage and this current, you can see if you want to draw the characteristics, see for plus and I, for V and I, for the positive region we are going to get the characteristics exactly as the SCR. So these are the characteristics that we are going to get a SCR. But for the negative voltage if you apply, we are going to get the characteristics of a diode. So these are the characteristics of a diode. So it is basically a connection of anti-parallel connection of a thyristor and also diode. So you can see clearly, yes, here two ways the current can pass. So it's a bidirectional device, and also here it can block positive voltage only but not the negative voltage. So it is a unipolar, and also here it is a semi-control switch. So basically it is a semi-control switch. In the both ways the current can flow, and it is a unipolar switch. These are the characteristics of the RCT. So now we'll discuss about the ASCR and the asymmetrical semiconductor, or we can say asymmetrical semiconductor rectifier. ASCR is nothing but here asymmetrical. SCR means here we are going to keep two thyristors. So we are going to keep two thyristors in such a manner. So therefore we can say that here, suppose here if you are going to keep the two symmetrical thyristors, so if you are going to keep two symmetrical thyristors in anti-parallel to each other, then what we are going to get? So you can see clearly here, this is called as a, suppose this is a forward blocking voltage. So this is the forward blocking voltage and this is the actual current, and this is the reverse blocking current. So therefore this is called as a reverse blocking region. So you can see clearly, if reverse braking voltage is equal to forward blocking voltage, then it is called as a symmetrical SCR. It is called as a symmetrical SCR. Otherwise, if both are not equal, then we are going to call it as the asymmetrical SCR. See, asymmetrical SCR means simply here it is a thyristor. It is only a thyristor. It is only a thyristor with, if forward braking voltage, if the magnitude value is equal to reverse braking voltage, then we are going to call it as the asymmetrical SCR. If it is equal, we are going to call it as a symmetrical SCR. If it is not equal, we are going to call it as the asymmetrical SCR. So basically it is a one thyristor only. But if the reverse braking voltage, is equal to forward blocking voltage, the magnitude value, then we are going to call it as the symmetrical SCR. Otherwise, if they are not equal, means it is a asymmetrical SCR. It is the only fundamental difference. So therefore, this is only one thyristor. It is only one thyristor, but only difference is if both are equal, it is called as symmetrical SCR. If both are not equal, then we are going to call it as a asymmetrical SCR. So now we will discuss about the diac. Diac means two anti-parallel combination of diodes. So if you go for the two anti-parallel combination of diodes, then we are going to call it as a diac. So let me assume this is the terminal 1 and this is the terminal 2. Because we don't know anode cathode exact values because both are anti-parallel. So because of that reason we are going to call one terminal as T1 and the other terminal as T2. So now we'll discuss about the triac. Triac is nothing but it's the anti-parallel combination of two SCRs is called as a triac. So if you are going to keep the two SCRs in anti-parallel, then we are going to take the cathode as a, we are going to take the gate as a common across the T1 and T2. That is the T1 and T2 we are going to call it as the triac. So therefore two anti-parallel SCRs with a common gate. So this is main terminal 1, main terminal 2. Because we don't know the exact value of anode cathode, so we are going to call one terminal as main terminal T1 and the main terminal 2. So in a shortcut way, the shortcut symbol of this one is like this, like two diodes like this we are going to keep. So this is a shortcut symbol, or you can say symbol of a triac. So this is a symbol of the exact symbol of a triac. Now we are going to learn about the diodes. Signal diode. Signal diode means it is a combination of P-type semiconductor and the N-type semiconductor. So here the voltage is VA and this is the IA. So this you are going to call it as the anode and this is the cathode. So here the voltage ratings of the signal diodes is in the terms of volts, whereas the current rating of the signal diodes is in the ratings of microampere to milliampere. Whereas the power rating of the signal diode is from milliwatt to watt. Whereas power diode Power diode means these diodes, these signal diodes are used in our analog electronics courses where they need a small amount of diodes. Whereas in power diodes means we need these devices in the power system, so we need higher ratings. So because of that, we are going to add an extra thing, that is n layer between the p and n. So we are going to say this as here p plus n minus and n plus. Plus means highly doped, minus means lightly doped. So this is VA or voltage across the anode and cathode, and this is the current IAK. So therefore simply we can say that we are going to add an extra n layer between the p plus and n plus. So therefore we are going to add an extra layer of n minus between the p plus and the n plus. So we are going to call this as the power diode, and it is going to have 3 layers. The voltage ratings is in the terms of kilovolts. It can now withstand huge value of voltage, and the current rating is from ampere to kiloampere, and the power rating is from watt to kilowatt. See, now you can see the readings has increased because by adding an extra layer of n minus between the p plus and n plus. So it can withstand huge value of voltage, huge value of current, and huge value of power rating. So you can see clearly now, if you draw the characteristics across the current and the voltage for both signal diode and the power diode, you are going to get in this manner. So you can see clearly this is called as the signal diode. So these are the characteristics of a signal diode, because it is going to have a small rating of voltage and the currents. So this we are going to get for a signal diode, but this is the graph we are going to get for a power diode. So power diode characteristics we are going to get like this, whereas this is signal diode characteristics. So you can see clearly the range is now increased. The range is now increased means the reverse bias voltage is increased, and also the forward bias voltage is also going to get increased for power diode when we come to a signal diode characteristics. So a small concept here is, suppose the power PG, suppose you are going to get graph in this manner, like maximum value of the PG is PGM, and this is turn on and this is the turn off. So power is only present for only on period but not for the off period in time interval of t. If they are asking what is the average power, say maximum value into T on by T. So T on by T we are going to get, this is called as a PGM into a T on by T is called as a duty period or duty cycle, which is PGM into D. So D is nothing but T on by T, it is called as a duty cycle. So this is the average value of the power. Suppose if you apply a DC voltage across a diode, then what are the characteristics that we are going to see? So now we are going to learn. So DC diode parameters means if you apply a DC voltage across the diode, and if you vary this voltage, what is the characteristic across the voltage and the current of a diode? Now we are going to see. So this is the anode current or anode to cathode current, and is the voltage across anode to cathode. So now I am going to draw the characteristics from IA to VA. So if you are going to give a positive voltage up to certain value, up to some certain value, cutting voltage, the current is 0. But after that it is going to get on, and now we are going to get in this manner. Means the voltage is nearly constant across the forward bias voltage and cutting voltage, and the voltage and the current is going to increase in this manner. So this is called as a forward bias region. In the reverse bias, if you give a negative voltage, across the diode, the leakage current is very small, but after that, if you give more than a reverse braking voltage, means the current will be very huge and the diode is going to get burned away. This is the characteristics of a diode. So this is for the forward bias and this is for the reverse bias. So VF is called as the forward voltage or the forward conduction drop, or simply we can say cutting voltage also we can say. So VF is called as the forward voltage or forward conduction drop, and VRB is called as the breakdown voltage or the reverse breakdown voltage. So VRB is called as the breakdown voltage or the reverse breakdown voltage. Means after this voltage, the current will be very huge value and the diode is going to get burned away. IA is called as the reverse saturation current or the reverse leakage current. Means during the reverse bias, that due to minority carriers, the current is going to get flow. It's a very small. That is called as a reverse leakage current, and it's a very small value. So now we are going to learn about the AC diode parameters. AC diode parameters means we are going to apply the AC source, and then we are going to draw the characteristics across the diode. What is the variation of the current and the voltage across the diode, that we are going to see. So this is the AC voltage, and this is the plus or minus VA and the current IA. So now I am going to draw the characteristics across this diode. So this is IA and VA. So this is VA and this is IA. So basically we are going to draw the characteristic with respect to time. So this is IA with respect to time we are going to draw the characteristics. So you can see clearly, for if you give a small amount of positive voltage, then the current is going to get increased and it is going to become a saturate. Means no matter if you further increase the voltage also, the current is going to become saturate. And then if you give a negative voltage, then the current is going to become, it is going to get decay and it is going to flow in the reverse direction. This is due to minority charge carriers, and then it is going to decay and decay and decay, and finally it is going to come to zero value. So this is called as the wave. Means a current cannot become instantaneously zero in a diode, because even if you give a negative voltage, it takes certain time in order to become current to become totally zero. That is the meaning of this one. So therefore you can see from this zero to this value we are going to assume. Suppose this is IRM, peak value in the reverse voltage applied. So IRM. So therefore now reverse current maximum value. Then at 0.25 of the IRM, then the time, this time from 0 to this value, we are going to call it as the TRR, reverse recovery time. So reverse recovery time means in this time all the minority charge carriers are going to lose the charge. So therefore this is called the reverse recovery time. And here from this maximum value to this instant, we are going to call it as the TB, and from 0 to this maximum value is called as the TA. So from 0 to this maximum value is a TA, and from maximum value to this value we are going to call as TB, and overall value is TRR. So therefore we can say here TF is called as the forward recovery time. So in this time it is going to get increased and come this one. This is the forward current IF. So therefore TF is called as the forward recovery time, and TRR is called as the reverse recovery time. So you can see clearly TR, reverse recovery time, is a summation of the TA plus TB, and there is also one more factor which is softness factor. Softness factor is the ratio of the TB by TA. So softness factor means it is the ratio of the TB by TA. So therefore TB is equal to S into TA. So in place of TB, if you substitute, we are going to get, in place of TB if you substitute this equation, we are going to get TRR is equal to 1 plus S into TA. So this is called as the reverse recovery time. So reverse recovery time is equal to summation of TA plus TB. The softness factor is the ratio of the TB by TS. So TB is equal to S into TA. If you can substitute in this equation, we are going to get TRR is equal to 1 plus S into TA. Then S is called as the softness factor. So if you want to know how much amount of charge present here in this graph, in this reverse recovery time, if you want to know how much amount of charge is present in the minority carriers, which is QR is equal to area under this graph, because I is equal to dq by dt, so Q is equal to integration of the current. So integration of the graph you need to do here. This is area of this one. It is nearly a triangle, so therefore half into base is nothing but here TRR, and height is IRM. So therefore half into IRM into TRR. So but dA by dt. So dA by dt is nothing but slope of this graph. The slope of this graph is nothing but dA by dt is nothing but here height is IRM and the base is TA. So therefore dA by dt is equal to IRM by TA. So IRM is equal to dA by dt into TA. Now QR is equal to half into, so IRM is equal to dA by dt into TA into this is TRR. But TA is equal to, see here, TA is equal to TRR by 1 plus S. So therefore TA is equal to TRR by 1 plus S. So if you do a simplification, we are going to get QR is equal to half into dA by dt into TRR square by 1 plus S. This is the actual equation. But for snap recovery diode, TB is nearly equal to 0. If TB is nearly equal to 0, then definitely we can say TRR is nearly equal to TA, or indicates S is nearly equal to 0. So if you substitute S is equal to 0 in this equation, we are going to get QR is equal to half into dA by dt into TRR square. So this is the equation for a snap recovery diode. Means the TB value is nearly equal to 0, then TRR is equal to TA, and S is equal to 0. So if you substitute in this equation, we are going to get this one. So QR is equal to half into dA by dt into TRR square. Well, now we will discuss about the silicon control rectifier. Silicon control rectifier means basically this is the symbol of a silicon control rectifier. Anode, cathode, and this is IA, and this is VA, and this is the gate. I have already told you SCR. SCR is a unidirectional device and also bipolar device, and here it is a semi-control device. All these things I have already discussed. So A is called as the anode, K is called as the cathode, and G is called as the gate. So now the symbol of the SCR is nothing but here PN. So PN. This is called as the SCR. So therefore SCR means PN. So therefore here PN means this is a n minus and this is n plus p. So therefore you can see clearly here we are going to add an extra p for a power diode. So we are going to get this symbol. So therefore if you add an extra p in for a power diode, we are going to get this SCR. So therefore PN PN. So this is highly doped and this is lightly doped. These are also highly doped. So therefore you can see clearly here this is anode, cathode and gate here. So this is junction J1, junction J2, junction J3. So so SCR has basically 3 junctions and 4 layers. So N plus means highly doped and N minus means lightly doped. So you can see clearly here N plus, this is thin and heavily doped. This is very thin in size, but this is heavily doped. Whereas P is thicker than N plus. So this is thicker than N plus means width is very high, but here width is very less. You can see clearly. Whereas N minus means thickest and less doped. This is even thickest means the width is very high and less doped. So you can see clearly this is very thin but heavily doped. This is very thicker than N plus, but it is also thicker. It is only thicker but normal doped. Whereas this one is very thick, very thick and compared to everyone, but this is lightly doped. So if you apply a forward voltage, what is going to happen? See, if you apply a forward voltage and the time you are not applying the gate current, if gate current is 0, then here it is going to means J1 and J3 are forward bias, but J2 is reverse bias. If you apply A to K as positive and negative voltage, so therefore A is positive and K is negative, then what is going to happen is V is positive. Then definitely what is going to happen is as J2 is reverse bias, definitely the current will be 0. So therefore you need certain voltage. The voltage is small amount of leakage current, but still after the breakdown voltage of the junction J2, the current is going to get flow with a minimum voltage drop. So this is called as the means here latching current. Here this is the latching current. So latching current is responsible for the turn on condition. So then for this breakdown voltage only, then only the current is going to get flow. So this is the characteristics of the forward conduction mode, whereas this is forward blocking mode. So this is the forward blocking mode and this is the forward conduction mode. In the forward blocking mode, junction J1 and J3 are the forward bias, whereas junction J2 is the reverse bias. Whereas in the forward conduction mode, everyone is conducting, so therefore J1, J2, J3 are the forward bias. Here, suppose if gate current is applied, if you are going to apply the gate current, then the junction J2 reverse breakdown voltage is going to get decay. So it is going to get decay if you are going to increase the value of the gate current. So now we can on it in a very small amount of time. So if you increase the gate current, the breakdown voltage is going to get decreased for the junction J2. So therefore we can easily go for the on position. So this is Ig1, Ig2 and Ig3. Here it is Ig0. So Ig3 is greater than, Ig2 is greater than Ig1. So IL is called as the latching current and IH is called as the holding current. So VDO is called as the breakover voltage when the gate current is 0. So VB3 is less than, VB2 is less than VB1. So therefore you can see clearly here, this is a forward conduction mode and this is a forward blocking mode. If you apply reverse voltage, if you apply negative voltage, then a small amount of leakage current is going to get flow, but still it's a very small. But if you apply more than reverse breakdown voltage, means in this reverse blocking mode, here what is going to happen is basically J1 and J3 are reverse bias, but J2 is forward bias. So because of this only, in minority carriers, because of this a smaller current is going to get flow, but nearly 0. This is called the reverse blocking mode. In the reverse blocking mode, J1 and J3 are the reverse bias, but J2 is forward bias. So because of this forward bias only, a small amount of current is going to flow. After the breakdown voltage of the junction J1 and J3, what is going to happen is these are also going to get conduct, but now because of this a huge amount of current is going to get flow and the SR is going to get damaged. So this is the reason we are not going to operate the SCR in the reverse conduction mode. Only in the 3 modes we are going to operate the SCR, which is forward blocking mode, forward conduction mode and the reverse blocking mode. See, in reverse blocking mode, junction J2 is on and J1, J3 are off, and J3 has less breaking voltage than J1. See, if you compare J1 and J3, if you compare, J3 has less breaking voltage than J1 because here the size is less, junction J3 size is less. So therefore here we can, as the junction size is very less, So therefore, here the breakdown voltage is very less. Whereas J1, the size is very high. The junction depletion width is very high. So therefore, here it needs huge amount of breaking voltage. So in reverse blocking mode, junction J2 is on and J1, J3 is off. So J3 has less breaking voltage when compared to J1 because J1 has high depletion width when compared to J3 in the reverse blocking mode. In forward blocking mode, if input voltage greater than breakover voltage of junction J2, then only it conducts when Ig is equal to 0. I have already told you in the forward blocking mode, J1, J3 is forward bias, but J2 is reverse bias. So whatever the applied voltage should be always greater than the breakover voltage of the junction J2, then only it is going to get conduct. Until that, the current will be 0. If you increase the gate current, then the breakover voltage of the junction J2 is going to get decay. As Ig increases, depletion width of J2 decreases, so breakover voltage decreases. I have already told you if the gate current increases, the depletion width of the junction J2 decreases, so therefore the breakdown voltage of junction J2 decreases. In forward conduction mode, all the junctions are conducting. Yes, I have already told you in the forward conduction mode, all the junctions are conducting, means everyone is forward bias. Turn off of SCR depends on input voltage or commutation circuit. See, turn off of the SCR depends on the input voltage or the commutation circuit. Only we can turn on the SCR by the user, but turning off is not under the control of the user. It can only means turning off of the SCR is only controlled by either the circuit or by external commutation circuit. So therefore, only by the input voltage or from the external commutation circuit only we can turn off the device, but not by the user. That is the reason we say it is a semi-controlled device. Only we can on the device but not the off. Where IL is called as the latching current and IH is called as the holding current. Minimum amount of anode current required to turn on the SCR means this is the minimum current which is required for the SCR to be conduct. And IH is called as the minimum amount of anode current below which SCR won't conduct. So this is the minimum value of anode current below which SCR won't conduct. So therefore we can say clearly here latching current and holding current. So latching current means minimum amount of anode current required to turn off the SCR, and IH means minimum amount of anode current below which SCR won't conduct. So latching current and holding current. Latching current is responsible with the turning on, whereas the holding current is responsible during the turning off. And always holding current is always lesser than the latching current. The easy way to remember is ABCD format: A, B, C, D, E, F, G, H, I, J, K, L. So H comes first rather than the L. So therefore, holding current is always lesser than the latching current. And latching current is nearly 2 or 3 times the holding current, but generally we are going to take the average of this one. 2 plus 3 by 2, which is 5 by 2 is 2.5. So therefore, latching current is nearly equal to 2 or 3, or it is 2.5 times the holding current. See now, if you try to draw the graph between the anode means VA and IG. So therefore, if you increase the IG, what is going to happen? If you increase the IG, that breakover voltage of the junction J2 is going to get decay. But if the current is increased, definitely the depletion width of the junction J2 is going to get decay. So therefore, the breakover voltage is going to get decay, and it is going to become smaller and smaller. And finally, it is going to remain constant. Irrespective of changing the gate current, still that junction J2 breakover voltage cannot change further than this, cannot decrease lesser than this value. So therefore, this is called as a finger voltage. Means the breakover voltage of the junction J2 can decay when current increases, but it cannot go beyond this value. Means it cannot decay beyond this value. There is a saturation for that one. This is called as a finger voltage. See, this reverse breakdown voltage cannot go lesser than this finger voltage, no matter whatever the increase in the current IG. So VF is called as a finger voltage. So for natural commutator thyristor or converter grade SCR has TQ is equal to nearly 50 microseconds to 200 microseconds. So this much amount of time is required in order to turn off the device. So for natural commutator thyristor or converter grade SCR, in this, if you give a natural way, means if you reverse the supply voltage, then naturally the circuit or the device or the switch is going to get turned off in this time, which is 50 microseconds to 200 microseconds. But for the commutator thyristor or inverter grade SCR has TQ 3 microseconds to 50 microseconds. Means if you give a combination circuit forcefully by external combination circuit, we want to turn off the switch in a very small amount of time, then we are going to keep the commutation circuit, force commutation thyristor. So by this we are going to turn off the device in a very short span of time, which is 3 microseconds to 50 microseconds. But naturally it takes around 50 microseconds to 200 microseconds. But forcefully we can go from 3 microseconds to 50 microseconds. So this is the meaning of this one. So natural commutative thyristor or contact grid SCR, by reversing the supply voltage, naturally it can turn off in 50 microseconds to 200 microseconds. But whereas force the commutative thyristor or inverter grid SCR, by using the external commutation circuit, we can forcefully off the device in 3 microseconds to 50 microseconds. So now we are going to discuss about the dynamic VI characteristics of the SCR. The dynamic VI characteristics of SCR. So dynamic VI characteristics of SCR means here we can see during the on characteristics, during the on period of SCR, we are going to see different diagrams. So this is the gate current. So I am going to increase the gate current in this manner. So I am going to increase the gate current from very smaller value to a very high value of I1, and after that I am going to keep it a positive value, means always a constant value. So this is 0.9 I1 and this is the maximum value. See, if you are going to increase the gate current, then definitely we can say the device is going to get on. So whenever the device is going to get on, we can say the voltage across the anode and cathode is going to get decay, because the switch is on. So therefore the voltage across the anode and cathode is going to get decay in this manner. So this is the way it is going to get decay in this manner. So now here, as the gate current increases during the turn on period, so this is called as the turn on period. In the turn on period, as the gate current increases and become constant, then definitely the voltage across the anode and cathode is going to get decay. Whereas the anode current, as the voltage across the anode and cathode is decaying, means the current should increase because it is switch on condition. So the current is going to increase in this manner. So this is the way the current is going to increase in the on period. So this is total period is on period. From here to here is called as the on period. So you can see clearly initially the current is 0 and it is going to slowly increase. It is going to slowly increase. So therefore now you can see clearly this is called as this is the maximum value of the current IF, and this is 0.1 IF and this is 0.9 IF. So therefore you can see clearly this is called as from 0 to 0.1 IF, this is called as the TD. The current, the anode current going from 0 to 0.1 IF is called as the TD, whereas the current going from 0.1 IF to 0.9 IF is called as the TR, whereas the current going from 0.9 IF to IF is called as the TP. So this whole process is called as the turn on. So turn on is a summation of TD plus TR plus TP. TD means anode current is going from 0 to 0.1 IF, whereas TR means the current is going from 0.1 IF to 0.9 IF, whereas TP means the current is going from 0.9 IF to IF. So the total on period is a summation of the TD plus TR plus TP. So this is called as a steady state condition. In a steady state condition, let me assume the current is a constant value because of some circuit parameters. As the current is constant, definitely we can say the voltage will be very minimum because the switch is already on. Suppose now I want to turn off the device. So by using some natural ways, we are going to, by reversing the supply voltage, we are going to off the device. Then what is going to happen? Then you can see clearly as the device is off, then current is going to decay. It cannot become instantaneously 0, so it is going to become slowly 0 in this manner. So therefore this is called as like this. So it is going to become slowly in this manner. So in this manner it is going to become slowly 0. So here from 0 to this value, so from 0 to this value we are going to call this as a reverse recovery time, and from this point to this point is called as the TGR, and overall summation of TR plus TGR is called as a TQ. So TQ is called as a device turn off time. So TQ is called as a device turn off time. Whereas from here to this point we are going to call it as the circuit turn off time. So therefore the summation of TRR plus TGR is called as the device turn off time, whereas TC is the overall circuit turn off time. This TC should be always greater than TQ, then only we can confirm that the device is totally off. So therefore when TC is greater than TQ, then only we can say that the device is totally off. Means we have to apply the reverse voltage more than the device time. So if you apply the reverse voltage across the device more than TQ, then only we can say the device is fully off. So TRR means if the current is 0 from 0 to 0.25 of IRM, then we are going to call it as the TRR. And from 0.25 IRM to 0, we are going to call it as a TGR. And this overall summation is called as the TQ, and this is the TC from 0 to 0 value. This is the circuit turn of time. So this is the voltage. So you can see clearly up to this time we have to give the voltage, reverse voltage. Up to this time we have to give the reverse voltage across the device. Then only we can confirm this one. So the reverse voltage should be given up to this time. Then only we can say the device is totally off. So always one thing is very important. Always the turn on time should be always lesser than the TQ than TC. So turn on time should be always lesser than the device turn off time, lesser than the circuit turn off time. So T on is always less than the device turn off time, lesser than the circuit turn off time. So turn on time of the SCR is always lesser than the device turn off time of the SCR is lesser than the circuit turn off time. So TD is called as the delay time. So TD is called as the delay time. TD means if the anode current is going to go from 0 to IF, it is called as the delay time. Whereas TR is called as the rise time, means if the anode current is going from 0.1 IF to 0.9 IF, it is called as the rise time. Whereas TP means it is called as the spread time, means it is the current is going from 0.9 IF to IF, it is called as the spread time. So therefore T1 is the summation of TD plus TR plus TP. TD means delay time, TR means rise time, and TP means spread time. So T1 is called as a turn on time. So turn on time is a summation of delay time plus rise time plus spread time. So TRR means reverse recovery time. So TR means reverse recovery time when the current is going from 0 to minus 0.2 minus 0.25 IRM, then we are going to call this as a reverse recovery time. In this time, charges are removed from J1 and J3. So because in the reverse bias, definitely J1 and J3. Reverse bias, J1 and J3 are the reverse bias and J2 is forward bias. So because of that, here in this time, charges are removed from J1 and J3 because they are reverse bias. So in this reverse recovery time, we are going to remove all the charges from J1 and J3 because they are previously forward bias. So therefore we can say in this time we are going to remove all the charges from the J1 and J3 because they are reverse bias. TGR is called as the gate recovery time. So TGR is called as the gate recovery time. It is the time for which the current is going from minus 0.25 IRM to 0. So in this time charges are removed from J2. So therefore in TRR we are going to remove the charges from J1 and J3, and in TGR we are going to remove all the charges from junction J2. So overall we can say we remove all the charges from J1, J2 and J3. So therefore the device turn off time is the summation of reverse recovery time plus gate recovery time. So TQ is called as the turn off time of the device, or device turn off time is the summation of the reverse recovery time plus gate turn off time. In this time we are going to remove all the charges from J1 and J3. In this time we are going to remove all the charges from the junction J2. So turn off time, or you can say device turn off time is the summation of the reverse recovery time on the gate turn off time or gate recovery time. Then circuit turn off time, TC is called a circuit turn off time for which reverse bias applied. So therefore TC is called circuit turn off time, means for this much amount of time we should apply the reverse voltage across the device. Then only we can confirm that always the device is perfectly off. If TC is greater than TQ, then device is 100% off. If TC is less than TQ, then device is not completely off, which is called as commutation failure. If TC is greater than TQ, then we can confirm that yes, the device is 100% off. But if TC is less than TQ means the device is not fully off. So therefore we can say it is a commutation failure. See, if Ig increases, means if if the rate of increase, if Ig increases means definitely in the same time the dIg by dt increases. Means if you are going to increase the Ig, means if you are going to increase more and more on value of current, then dIg by dt goes on increases, means slope increases. Then definitely if the slope increases, what is going to happen? The TD value decreases. If the slope increases, then definitely TD decreases. If TD decreases, T1 decreases. So therefore if you want to decrease the turn on time, if you want to decrease the turn on time of SCR, then what you have to do is basically you have to increase the gate current. So by increasing the gate current, the slope of the gate current increases. So therefore TD is going to get decreased. So therefore because of that, overall value is going to get decay. So by increasing the gate current, we are going to decrease the turn on time. So width of gate pulse must be always greater than T on. So then only we can confirm that device is turn on. So therefore the width of gate pulse must be always greater than turn on. Then only we can we can confirm that the device is perfectly turned on. See, always whatever the width of gate pulse, the width of gate pulse should be always greater than T on, then only we can confirm that the device is turned off. And always here you have to apply the reverse voltage across the device, which is TC should be always greater than TQ, then only we can ensure that the device is fully off. So these are the two important points. Always the width of the gate pulse should be always greater than T on, then only we can ensure the device is 100% on. And also the circuit turn off time means the device time for which the reverse bias voltage applied across the device should be always greater than the TQ device turn off time, then only we can ensure that the device is 100% off. So now we will discuss the different triggering methods to turn on the SCR. So different triggering methods to turn on the SCR. Forward voltage. The first method is the forward voltage. If Ig is equal to 0 and when anode to cathode voltage is greater than the breakover voltage, then only the device gets on. See, forward voltage means by using the forward voltage also we can turn on the SCR. See, during the forward voltage I am going to assume the gate current is equal to 0. Then if anode to cathode voltage if applied is greater than the reverse breakdown voltage of junction J2 or breakdown voltage, then definitely we can say that the device is turned on. This is called as the by using the forward voltage we are going to turn on the SCR. The second method is the dV by dt triggering. So dV by dt triggering means here if VAK greater than 0 means if you are going to apply anode to cathode voltage is greater than 0, then definitely J1 and J3 are forward bias and J2 is equal to reverse bias. So it is going to act like a capacitor, as junction J2 is going to act like a reverse bias means there is a depletion width. So because of that a small amount of immobile charges are going to present in the depletion width. So because of that it is going to act like a capacitor. So capacitor current is equal to C into dV by dt. So IC is equal to C into dV by dt. So this is a general expression of a current in a capacitor. So I is equal to C dV by dt. Here IC is equal to IA in this case. So IA is equal to C into dV by dt. So therefore here voltage is equal to anode to cathode voltage. So if you take this C downward, we are going to get dV by dt is equal to IA by C. So when Ij is greater than or equal to IL, then what is going to happen? If anode current is greater than or equal to latching current, then we can say that dV by dt is always greater than or equal to IL by IC. If dV by dt is greater than or equal to IL by IC, then we can say that the device is going to get turned on. So therefore, if rate of change of anode to cathode voltage is greater than or equal to IL by C, the threshold value or the maximum value is IL by C. If this is the case, then we are going to say that yes, the device is going to get turned on. So therefore, because the current is greater than the latching current. So therefore, normally the dV by dt, normally it will be around 20 to 500 volt per microsecond. This is the normal range of dV by dt, which is 20 to 500 volt per microsecond. So the threshold value is IL by C. So whenever the rate of change of anode to cathode voltage, if it is greater than or equal to threshold value, then we can say that yes, the device is going to get turned on. So this is called as the dV by dt triggering. So the third method is the light triggering. When the light hits junction J2, as light has some electrons and photons, it neutralizes the junction J2. So depletion layer of junction J2 decreases. So suppose if you are going to hit the junction J2 with the help of light, as the light is going to have some electrons and photons, it is going to neutralize the junction J2. So depletion layer of junction J2 decreases. So now we can easily turn on the device. This is called the light triggering. This by using the light, we are going to point out at the junction J2. So because of that, as the light is going to have some electrons and photons, it is going to hit the junction J2. So because of that, the junction J2 width is going to get decreased. So depletion width decreases means breakdown voltage decreases. So now it can easily turn on. Another method is thermal triggering. When the temperature around junction J2 increases, the electron movement increases. So depletion width decreases. So if you increase the temperature around the junction J2, then definitely that electron movement is going to get increased. If you increase the temperature, electrons are going to move freely. So therefore, they are going to increase their movement. So therefore, the depletion width layer decreases. So therefore, now it can easily trigger or it can easily be on. So therefore, when the temperature around junction J2 increases, the electron movement increases. So depletion layer width decreases. So it can easily turn on. And one more method is gate triggering. In continuous gate triggering, gate current is applied continuously even under IA is greater than or equal to IL, so loss occurs in this case. This continuous gate trigger means you are going to apply the gate current even when the SR is on. So by this, what is going to happen? Even when the SR is on, still if you are going to apply the gate current means you are going to get the losses. See, no need to apply the gate pulse when the device is on, because the turning off means there is no way of offing the device. It is not in our control. So therefore, you don't have to apply the gate current when the device is on. So in pulse triggering, gate current is given in terms of pulse width. When pulse of width T1 is greater than or equal to T1 minimum, in this case T1 minimum IA reaches IL. So we are going to give the pulse in such a way that in this time period the current is going to reach the latching current. So means we are going to give the pulse width of this gate current in such a way that in this time anode current is going to reach the latching current. Then we can ensure that yes, the device is on. So therefore we can say in pulse triggering, gate current is given in terms of pulse width, and when pulse of width T1 is greater than or equal to T1 minimum, in this T1 minimum IA reaches IL. Means always the pulse width should be always greater than or equal to T1 minimum. Means in this T1 minimum the anode current is going to reach the latching current. Then only we can ensure that the device is turned on. So therefore we can say clearly, either you apply continuous gate triggering or like pulse gate triggering, we can ensure that the device is going to get on. So the different ways are the forward voltage method, dV by dt triggering, light triggering, thermal triggering, and gate triggering. So these are the 5 methods by which we are going to turn on the SCR. The first method is the forward voltage, and the second method is dV by dt triggering, and the third one is the light triggering, and the fourth one is the thermal triggering, and the fifth one is the gate triggering. So by all these trigger methods we are going to turn on the SCR. So now we will discuss the SCR protection. See how to give the protection for the SCR. So this is an SCR. So we are going to keep some certain elements across the SCR to protect it from various conditions. So parallel RC. So we are going to keep the parallel RC. Means this is the parallel RC. Means in a series. See, this is the RC is a series, but we are going to keep in parallel RC. So this is the basically parallel RC. So to remove unwanted noise from the gate supply. So this parallel RC we are going to keep across this gate in such a manner. So therefore, to remove unwanted noise from gate supply, because if the supply has some unwanted noise is going to have high frequency. At high frequency, the capacitor is going to get short circuit. So whatever the noise is going to get, it is going to bypass away from here. So they can't enter this SCR. So therefore, the parallel RC is used to remove the unwanted noise from the gate supply. Whereas series RC, this is a series RC, it is going to limit the dV by dt protection, because in a capacitor the voltage cannot change instantaneously. So therefore, because of this we are going to keep the RC. So because of that we are going to limit the dV by dt protection. Means if there is any sudden change in voltage, we can protect it. Means we don't want to do that. We don't want to have to a sudden change. So therefore it is going to limit the dV by dt protection. Whereas this diode for negative voltage protection. So therefore we are going to give the diode. Means if you give a positive or negative, then only it is on. If you give a negative voltage across the gate supply, gate and this cathode, then definitely it is off. So therefore it is going to protect from negative voltage. So diode is used for protection against the negative voltage across the gate and cathode. Fuse, it protects from large current. So therefore fuse is going to protect from large currents. If there is a large currents are going to enter, then it is going to get protected. So therefore from large currents, so this is basically a fuse, then fuse is going to protect from large currents. So whenever the current is greater than a rated current, this fuse is going to get blow off. So therefore it is going to protect at large currents. So varistor for higher voltages R is low, so it protects from over voltages made by zinc oxide. So varistor we are going to make from zinc oxide. Basically we are going to make varistor from zinc oxide. And the special property of this one is at high voltages or over voltages, this resistance will be ideally 0 or low. So therefore whatever the current is bypassed from this varistor. So it is going to protect this SCR from over voltages, because varistor is made from zinc oxide. As the voltage increases, here the resistance decreases. So therefore it is a depending upon or sensitive of voltage. As resistance decreases, the overall current can bypass here. So it is going to protect from over voltages. Inductor is basically it is going to protect at dI by dt protection. Means a sudden change in current, it can protect from sudden change in current. So inductor means it is going to protect under the sudden change of current. Heat sink. So this is called as a heat sink. So we are going to use heat sink to control the temperature, and it is made by aluminum. So therefore we are going to heat sink is used to control the temperature. Means whatever the temperature of the SCR, it is going to control with the help of this heat sink, and it is basically made by aluminium. And there is a Zener diode. So Zener diode for gate voltage protection to keep fixed voltage. So we see, suppose if there is a variable voltage, we want only fixed voltage. So because of that, we are going to use the Zener diode to keep a fixed voltage across this gate and cathode. Always to keep a gate and cathode as a fixed voltage, we are going to use the Zener diode. So here parallel RC to remove the unwanted noise from the gate supply, and whereas the series RC to limit the dV by dt protection, whereas the diode we are going to keep used for negative voltage protection across the gate source, gate and cathode voltage, and whereas fuse it is protects from large currents, whereas varistor for higher voltages R is low, so it protects from over voltages made by zinc oxide, whereas inductor is from di by dt protection, and heat sink to control temperature, and it is made by aluminium, whereas Zener diode for gate voltage protection to keep fixed voltage. I am repeating again, the parallel RC to remove unwanted noise from gate supply, whereas series RC to limit the dV by dt protection, whereas the diode to for negative voltage protection, and whereas fuse to protect from large currents, whereas varistor for higher voltages R is low, so it protects from over voltages, and it is made by zinc oxide, whereas inductor it is protects from di by dt protection, whereas heat sink to control temperature, and it is made by aluminium, whereas Zener diode for gate voltage protection to keep fixed voltage. So these are some of the devices we are going to keep across the SCR to protect from various conditions. So same thing I have written, parallel RC to remove unwanted noise from gate supply, series RC to limit dV by dt protection, and diode for negative voltage protection. Fuse protects from large currents, varistor for higher voltages resistance is very low, so it protects from over voltages, and is made by zinc oxide, and inductor di by dt protection, and heat sink to control temperature, and it is made by aluminium. Zener diode for gate voltage protection to keep fixed voltage. So now we'll discuss about the heat sinks. So this is basically a heat sink. I have already told you about the heat sink. It is basically made by aluminium. So it is going to have 4 casings. Like this, it is going to have like 4 junctions. J, C, S, A. J is called as a junction, C is called as a casing, S is called as a sink, and A is called as an ambient. So JCSA. So JCSA. J means junction, C means casing, S means sink, A means ambient. Junction, casing, sink, ambient. Always the temperatures Tj is greater than, Tc is greater than, Ts is greater than Ta. Because this is near the atmosphere, so this temperature will be always less. But this is across the SCR, so its temperature is always higher. So therefore, Tj is greater than, Tc is greater than, Ts is greater than Ta. J means junction, C means casing, S means sink, A means ambient. So take 4 points, Tj, Tc, Ts and Ta. So these are the 4 resistance. This is resistance across the junction J and junction C, resistance across the junction C and junction S, and resistance across the junction S and junction A. So these are the 3 resistors. So this is called as the, see, this is the amount of power. So this much amount of incoming average power which is going to flow from J to A. So therefore now P average is equal to, so we can go from this, like this is the voltage difference and this is the resistor. So therefore Tj minus Tc by theta Jc is equal to Tc minus Ts by theta Cs is equal to Ts minus Ta by theta Sa is equal to Tj minus Ta by Tjc plus Tcs plus theta Sa. So we can go like this. So Prg is equal to Tj minus Tc by theta Jc is equal to Tc minus Ts by theta Cs is equal to Ts minus Ta by theta Sa is equal to Tj minus Ta by theta Jc plus theta Cs plus theta Sa. So this overall I am going to assume it is Tja. So Tja is equal to theta Jc plus theta Cs plus theta Sa. So this is the equation. This equation is very much useful to solve the questions. See, now we will compare the thermal system and the electrical system. See, heat flows. In the thermal system, heat flows we are going to represent by symbol Q, where Q means heat means nothing but the unit of heat means joules. Similarly, in electrical system, charge flows we are going to represent by small q. Small q unit is coulombs. Here, heat transfer rate. Heat transfer rate means here P average. So average power is nothing but watts. Here current is nothing but I. So therefore I is nothing but ampere. So here I is the dq by dt. Similarly, power is the energy by time. So therefore it is a differentiation of energy with respect to time. So therefore PRH is equal to d energy by dt. Similarly current is equal to dq by dt. So here heat flows, here charge flows, here heat transfer rate or average power flows, here current flows. Here temperature difference, the unit is degree Celsius. Here potential difference, the unit is volt. Here thermal resistance, it is called thermal resistance, and its unit is here voltage by resistor, right? Voltage by current. So voltage means here potential difference or temperature difference, by current is here watts. So here electrical resistance is volt per ampere. So this is the way you can compare them, thermal system and the electrical system. Here heat flows, here charge flows. Here power flows, here current flows. Here temperature difference, here voltage difference. Here thermal resistance, here electrical resistance. So here heat flow means Q, yes, capital Q. Charge flow means small q. Here power flows or heat transfer rate, here current flows, here P average and I. Here temperature difference means here potential difference. Here thermal resistance means here electrical resistor. So thermal resistor is represented by symbol theta, whereas electrical resistance is represented by symbol capital R. Here temperature difference is represented by symbol capital T. Here potential difference is represented by symbol capital V. So here heat flow means capital Q, charge flow means small q. Here heat transfer rate or average power means capital P average. Here the current flows means current I. Here always P is directly proportional to I square. So I is directly proportional to under root over P. So I is directly proportional to P is nothing but Tj minus Ta by theta Ja. So if Ta decreases, as Ta decreases, this overall value increases. So therefore current rating of thyristor increases. So if you want more and more rating of thyristor, this ambient temperature should be always less. So by keeping the SCR in a very less amount of temperature, then we can use for higher ratings. So by using the SCR in a very low temperatures, then we can go for high rating of SCR. So this is the meaning of this one. So now we are going to discuss about the turn off methods of thyristors. By what way we are going to turn off the thyristor? Commutation means process by which turn off thyristor. There are two commutation ways for turning off thyristor. Commutation means basically the meaning of commutation means it's a process of turning off any device. So commutation means it's the basic process of turning off any device. There are basically two types of commutation ways of turning off a thyristor. There are the natural commutation and the forced commutation. By natural way you can turn off the SCR, and also by forced way also you can turn off the thyristor. Natural commutation. Based on supply voltage, the device will turn off automatically. It is called as the natural commutation. Example is a supply. So if you give a negative pulse, if you give a negative voltage across the anode to cathode, then definitely we can say the device is going to get turned off. It's a natural way. Means by a circuit voltage only we are going to turn off the device. That is called as the natural commutation. Then I will discuss about the forced commutation. During DC supply, thyristor is on, so we force it to turn off. This is called as forced commutation. See, if you take a DC supply, then definitely the thyristor will be always on, but we want it to off. Then we are going to keep an external circuit across the SCR. The circuit is going to ensure that this device is going to get turned off. Means the circuit is going to make the negative voltage across the thyristor in such a way, or the current in the anode to cathode is lesser than the latching is lesser than the holding current. So by this process it is going to turn off the thyristor in a forced manner. So this is called as the forced commutation. Means by keeping an external circuit, we try to bring the negative voltage or current lesser than the holding current. So by this process we try to make the device to turn off. So this is called the forced commutation, and the natural commutation, the forced commutation. So we learn natural commutation means by circuit voltage only we try to turn off, and the forced commutation means by keeping an external circuit we try to turn off the device. So natural commutation and forced commutation. In phase control rectifiers uses natural commutation for turning off thyristors. So here in phase control rectifiers we use the natural commutation to turning off the thyristors, whereas choppers uses forced commutation technique for turning off thyristors. In phase control rectifiers we use the natural commutation process to turn off the device, whereas in choppers we try to use the forced commutation to turn off the thyristors. In AC voltage controllers uses natural commutation for turning off thyristors. In AC voltage rectifiers, in AC voltage controllers also we are going to use the natural commutation for turning off the thyristors. In inverters we use the forced commutation technique for turning off the thyristors. So in step down cycloconverter, which is FH minus FL, so highest frequency minus lowest frequency, uses natural commutation for turning off thyristors. The step up cycloconverters means it is going to increase the frequency from FL to FH, uses forced combustion technique for turning off thyristors. Step down cycloconverters means it is going to reduce the frequency from high to low. That is going to use the natural combustion for turning off thyristors, whereas step up cycloconverters means it is going to increase the frequency from FL to FH. Then it is going to use the forced commutation technique for turning off thyristors. So natural commutation of turning off thyristors is used in phase control rectifier, AC voltage controller and step down cycloconverter, whereas forced commutation way of turning off the thyristors is used in choppers, inverters and also step up cycloconverter. The natural way of turning off the thyristors is used in phase control rectifiers, AC voltage controller and step down cycloconverter, whereas the forced commutation way of turning off the thyristors is used in choppers, inverters and step up cycloconverters. So now we are going to learn about the designing of snubber circuit. So designing of snubber circuit. This is called as a snubber circuit. It is a consisting of series RC circuit. So this is going to control the rate of change of voltage across the, or it is going to control the dV by dt triggering or limit the dV by dt triggering across the thyristor. So we are going to keep across parallel across the thyristor like this. So let me assume this is the load and this is the LS inductance. So this is the supply voltage Vs. So here dVA by dt maximum value and dIA by dt maximum value known for thyristor. So we know the what is the maximum rate of change of voltage and maximum rate of change of current for a thyristor we are given, means they are already known for a given thyristor. So the maximum rate of change of voltage across the thyristor and the maximum rate of change of current across the thyristor, we can easily get to know the data. So Vs also we know. So we know the value of Vs, we know the value of this value and this value, we already know. So now we have to calculate what is the value of Rs, Cs and remaining things that we need to figure out. So here when the device is on, what is going to happen, which is Vs is equal to Ls into. So Ls into means this is the, see what we are going to assume is what are the voltage that is going to drop across the voltage is going to drop across the inductor Ls. So therefore Vs is equal to Ls into dIA by dt maximum value. So therefore Ls is equal to Vs by dIAt by dt maximum value. So this is the equation we are going to get. So Ls is equal to Vs by dIA by dt maximum value. Whereas Rs is equal to, see Rs is equal to rate of change of maximum value of anode to cathode voltage by rate of change of maximum value of anode to cathode gate current. So therefore Rs is equal to dVA by dt maximum value by dIAt by dt maximum value. So therefore here you can replace, this equation. So therefore this you can replace 1 by dIAt by dt maximum value, you can replace which is Rs by dVA of t by dt maximum value. So from this equation also we can simplify this one and we are going to get like this. So Ls is equal to Vs by dIA by dt maximum value, whereas Rs is equal to dVA by dt maximum value by dIA by dt maximum value. So from these two equations we know the value of Ls, we know the value of Rs. So now we need to find what is the value of Cs. So the general equation, which is Rs is equal to 2 zeta into under root over Ls by Cs. So therefore here simply we can say, as here we are, see as the device is on, we are going to get like this. Rs is equal to 2 zeta under root over Ls by Cs. See, as the device is a series RLC circuit, so it's a series RLC circuit, right? So zeta is equal to R by 2 under root over C by L. So by using that formula, if you simplify, we are going to get Rs is equal to zeta under root over Ls by Cs. So this is for a series RLC circuit, we are going to get zeta is equal to R by 2 under root over C by L. So by using that formula, we are going to get like this. Rs is equal to 2 zeta under root over Ls by Cs. So we know the value of Ls, we know the value of Rs. So now we can easily get the value of Cs from this equation. We are going to generally choose zeta is equal to 0.65. So by using the zeta is equal to 0.65, we can get the value of Cs also. For practical purpose, choose Rs more than calculated value. See, for practical purpose, you have to choose the value of Cs which is greater than the calculated value. And based on that, find Ls. And based on that, find the value of Ls. And choose Cs lesser than the calculated value. For practical purpose, choose RS more than the calculated value. So therefore, for practical purpose, choose RS more than the calculated value, and based on that find LS, and choose CS lesser than the calculated value. So therefore, see here. So based on this, we are going to get the value of CS. So for practical purpose, choose RS more than the calculated value. So choose the value RS more than the calculated value, and based on that find the value of LS, and choose CS lesser than the calculated value. So here choose CS lesser than the calculated value, and then choose the value of RS greater than the calculated value, and keep it in the LS and try to get the value of LS. So Vs is called as the DC value for DC voltage and maximum value for AC voltage. It's a very important find. And Vs is called as the DC value for DC voltage and maximum value for AC voltage. It's a very important point. This is the maximum value for AC voltage. It's not a RMS value. It is a maximum value. So it is a DC value for a DC voltage, and it is a maximum value for AC voltage. It's a very important point. So now we are going to discuss about the response in the LC circuit with DC excitation. So suppose if you are going to give a DC supply to a pure LC circuit, then what is the nature of the current and the voltage across the inductor and the capacitor? All these things now we are going to learn in a detailed manner. So initial condition I am going to assume means before I close the switch at t is equal to 0, I am going to assume that the voltage across the capacitor is having some initial voltage of Vc0. And similarly current in the inductor at the initial condition I am going to assume it 0. So therefore I am going to assume that initial voltage across the capacitor when the switch is open, which is Vc0, and the initial current in the inductor is 0 when the switch is open. So with these conditions, now I am going to close the switch, and then I want to know what is the value of the current expression, voltage across the inductor and the voltage across the capacitor. So by KVL, if I apply the KVL in this closed loop at t is equal to 0, I am going to get Vs is equal to, so plus Vs minus VL minus Vc is equal to 0. So Vs is equal to VL plus Vc, but VL is equal to L into di by dt. So therefore I am going to get the expression which is Vs is equal to Vc plus L into di by dt, whereas I is equal to C into dVc by dt. This is the current and voltage across the capacitor relationship. So therefore finally I am going to get, in place of I, if you go for the first derivative, so di by dt is equal to C into d square Vc by dt square. So you are going to get finally Lc d square Vc by dt square. So this is the expression finally you are going to get, which is Vs is equal to Vc plus Lc into d square Vc by dt square. So now I am going to apply the Laplace transform on both the sides. Then I am going to get here I am going to get, which is Vc of s plus Lc into s square Vc of s minus s into Vc of 0 minus Vc dash of 0 minus plus Vc of s is equal to Vs by s. Because it's a constant voltage, I am going to get Vs by s. So I am going to take this C to the downward. I am going to get Vc dash of t is equal to Ic of t by C. So if I want to know what is the value of the at t is equal to 0, what is the value of Vc at t is equal to 0, if I want to know, I can substitute this equation. So Vc dash of 0 is equal to Ic of 0 by C, but Ic of 0 is nothing but it is 0, because here Ic of 0 is nothing but here I of 0, so therefore both are equal, so therefore current is 0, so therefore we are going to get final 0. So therefore this equation we are going to get as 0. So only these two terms are going to get present. So therefore Lc into s square Vc of s minus s into, but Vc of 0 is nothing but Vc0 plus Vc of s is equal to Vs by s. If you take Vc of s as a common in these two terms, we are going to get Lc s square plus 1 is equal to Vs by s plus here LCS Vc0. So you can see clearly, if I take Vc of s, I am going to divide by here 1 plus s square Lc on both sides. I am going to get V of s by sc into LCS square plus 1 plus LCS Vc0 by LCS square plus 1. So now Vc of s is equal to here Vs by s into LCS square plus 1. Here what I am going to do is simply, here I am going to take 1 by LC as a common, then I am going to get here LC, if I take as a common, LC cancels, I am going to get s into Vc0 by s square plus 1 by LC. So now I am going to split this into two partial fractions, which is a by s plus, here I am going to do into partial fractions. I am going to get finally here Vs by s plus as plus b by LC s square plus 1 plus s into Vc0 by s square plus 1 by LC. So if you solve this equation finally we are going to get A is equal to minus LCVS and V is equal to 0. So this is the what we are going to get finally after substituting this one. So I have divided this into two partial fractions and I have done the simplification. Then I am going to get the final value of A is equal to minus LC Vs and V is equal to 0. So if you substitute A is equal to minus LC Vs and V is equal to 0 in this equation, above equation, we are going to get in this format. So therefore finally Vc of S is equal to Vs by S minus, here if you take LC as a common, we are going to get Vs into S by Sk plus 1 by Lc plus S into Vc naught by Sk plus 1 by Lc. So then I am going to assume which is omega naught is equal to 1 by under root over Lc. I am going to assume which is omega naught is equal to 1 by under root over Lc. So if you go for the inverse Laplace transform, then I am going to get Vc of t is equal to Vs minus Vs into cos of omega naught t plus Vc naught into cos of omega naught t. Because if you go for the Laplace transform of this one, we are going to get S by S square plus omega naught square, and this we are going to get here S by S square plus omega naught square. So like this we are going to get. So finally this is the equation we are going to get where omega naught is equal to 1 by under root over Lc. So if you do a common things of these two things, we are going to get Vc of t is equal to Vs into 1 minus cos omega naught t plus Vc naught cos omega naught t. So this is the expression of the voltage across the capacitor. So Vc of t is equal to Vs into 1 minus cos omega naught t plus Vc naught cos omega naught t, where omega naught is equal to 1 by under root over Lc. So current, if you want to know what is the current in the circuit, current is equal to I of t is equal to C into dVc of t by dt. So this is the current and voltage expression. So therefore you know the value of Vc of t, just to the differentiation and multiply by C. Finally you are going to get I of t is equal to under root over C by L into Vs minus Vc naught sin omega naught t. So these are the very two important expressions. So therefore Vc of t is equal to Vs into 1 minus cos omega naught t plus Vc naught cos omega naught t, whereas I of t is equal to under root over C by L into Vs minus Vc naught sin omega naught t. And if you want to know what is the value of the VL of t, so VL of t is equal to Vs minus Vc of t. So if you solve this one, finally we are going to get, or you can go for another format also, VL of t is equal to L into di by dt. So we know the value of I, do the differentiation and multiply with respect to L. So finally we are going to get VL of t is equal to Vs minus Vc naught cos omega naught t. So this is the expression we are going to get finally. VL of t is equal to Vs minus Vc naught cos omega naught t. So Vc of t is equal to Vs into 1 minus cos omega naught t plus Vc naught cos omega naught t, whereas I of t is equal to under root over C by L into Vs minus Vc naught sin omega naught t, whereas VL of t is equal to Vs minus Vc naught cos omega naught t. So these are the three important relations. So we know the value of Vc of t, VL of t and I of t. So Vc of t is equal to Vs into 1 minus cos omega naught t plus Vc naught cos omega naught t, whereas I of t is equal to under root over C by L into Vs minus Vc naught sin omega naught t, whereas VL of t is equal to Vs minus Vc naught cos omega naught t, whereas omega naught is equal to 1 by under root over Lc. So now we are going to see some special conditions. Under zero initial conditions, what is going to happen? Under zero initial conditions means, suppose if I am going to assume that initial capacitor voltage is equal to 0, then what are the things we are going to get? Then Vc of t, see wherever Vc naught is there, just substitute 0, we are going to get Vs into 1 minus cos omega naught t, and I of t is equal to Vs into under root over C by L into sin omega naught t, where omega naught is equal to 1 by under root over Lc. So this is the thing that we are going to get when Vc naught is equal to 0. Suppose the another special condition is source free circuit. Source free circuit means the supply voltage is 0. It means Vs is equal to 0, but the capacitor voltage is there, which is initial capacitor voltage is not 0, which is Vc of 0 is equal to Vc naught. Then what is going to happen? So in the above general expression, substituting Vs is equal to 0, we are going to get Vc of t is equal to Vc naught into cos omega naught t, and I of t is equal to minus Vc naught into under root over C by L into sin omega naught t. So this is the expression we are going to get. Vc of t is equal to Vc naught into cos omega naught t plus I of t is equal to minus Vc naught into under root over C by L into sin omega naught t. Means we simply the current is going to reverse its direction. See, initially the current is going from plus to minus, but now current goes from, see, current is now, see here in the previous case that the capacitor is equal to absorb the power, but now it is going to generate the power. So Vc of t is equal to Vs into 1 minus cos omega naught t plus Vc naught cos omega naught t, and I of t is equal to under root over c by L into Vs minus Vc naught sin omega naught t, whereas Vl of t is equal to Vs minus Vc naught into cos omega naught t. So these are, and omega naught is equal to 1 by under root over Lc. These three are the very important relationships that you should remember to solve the LC circuit questions. So now we are going to see the diode LC circuit with zero initial conditions. Diode LC circuit with the zero initial conditions means we are going to keep a diode and the zero initial conditions. Then what is the nature of the current, voltage across the inductor, voltage across the capacitor, everything now we are going to see. So now before I close the switch, I am going to assume that the capacitor voltage is 0, the capacitor voltage is 0, and suppose if I close the switch, then what is going to happen? I have already told you the expression of the capacitor voltage, which is here the Vc naught is equal to 0, so finally you are going to get Vs into 1 minus cos omega naught t, and I of t is equal to Vs into under root over c by L into sin omega naught t, whereas Vl of t is equal to L into di by dt is equal to Vs into cos omega naught t. So these are the three expressions we are going to get if we keep Vc naught is equal to 0 in the general expressions. So you can see clearly, see, current is going to become negative when omega naught t is equal to pi. When omega naught t is equal to pi, after that the current is going to become negative. But current cannot be negative because the diode will get open when the current is negative. So therefore the circuit is going to conduct only when omega naught t is equal to pi. So therefore the circuit is going to get conduct only from t 0 less than t less than equal to pi by omega naught. So only for this region only the current is positive, so therefore the diode is going to get conduct. After that the current will be negative, so therefore the diode is going to get off. That is the meaning of this one. So these equations are going to hold only in the region of 0 less than equal to t less than equal to pi by omega naught. So now we will see at what the values of each and everything at the different times instance. Suppose at omega naught t is equal to 0, then what is the value of Vc naught, I of naught and Vl of naught? So if you substitute omega naught t is equal to 0, then Vc of 0 we are going to get finally 0, and I of 0 you are going to get 0, and Vl of 0 you are going to get Vs. So these are the values you are going to get at omega naught t is equal to 0. So if you substitute here, you are going to get these values. At omega naught t is equal to pi, if you substitute omega naught t is equal to pi in this expression, so cos pi is nothing but we are going to get minus 1. So minus of minus is plus 1. So 1 plus 1 is 2. So 2 into Vs. So Vc of pi is equal to 2 Vs. And if substitute in this expression, sin pi is nothing but you are going to get 0. So therefore I of t will be equal to 0, or I of pi is equal to 0 at that instant. And Vl of pi, if you substitute pi, we are going to get minus. So therefore you are going to get negative 1 means minus Vs. So you are going to get minus Vs. And see at what is the instant at just pi plus, at just the value of pi plus. Yes, I have already told you the circuit is now going to become open. So capacitor voltage cannot changes. So it will be same as the previous case. So therefore here the capacitor voltage will be same as the previous one, which is Vc is equal to 2 Vs as the just instant at pi. So 2 Vs. And now here the diode voltage, because the circuit is open, and circuit is open, then what is the value of this Vl? Because the current, as the circuit is open, then the current is 0. As the current is 0, the inductor voltage is also equal to 0. So therefore the inductor voltage will be 0. That is the instant we are going to get. At pi plus the inductor voltage is 0. And now based on this we have to find what is the value of the diode voltage. So by applying the KVL, we are going to get Vs is equal to Vd plus Vl plus Vc. But Vd is equal to Vs minus Vl minus Vc. So at pi plus Vl is equal to 0 and Vc is equal to 2 Vs. So finally we are going to get Vd is equal to minus Vs. So Vd is equal to minus Vs we are going to get. But from 0 to pi is whenever the t is ranging from 0 to pi by omega naught, the diode is going to conduct. So diode voltage is 0. Up to that instant, after that it is minus Vs for all the time. Now with this data we are going to plot the graph. So you can see clearly that diode voltage is minus Vs. So we can say this is the maximum voltage it is experienced by the diode. So Vs is the maximum voltage which is experienced by the diode. So this is called as the peak inverse voltage of the diode. So the peak inverse voltage of the diode is Vs. So peak inverse voltage of the diode is Vs. So if you draw the graph of I of t, that is Vs into under root over c by L sin omega naught t, this is the expression only holds from 0 less than or equal to t less than or equal to pi by omega naught. Means here omega naught means only up to pi we are going to get. Only from 0 to pi we are going to get a sine graph, and the maximum value is Vs into under root over C by L. So after that it will be always 0. The current will be always 0 for steady state. No matter whatever the time, from here it will be always 0. And VL of t is Vs into 1 minus cos omega naught t. This is the expression which is also only from 0 less than or equal to t less than or equal to pi by omega naught. So omega naught t means here at 0 we are going to get Vs, and at pi we are going to get minus Vs. So this is the way we are going to get, and after that it is always 0. Irrespective of the time, it is always equal to 0. Whereas capacitor voltage, the capacitor voltage expression is Vs into 1 minus cos omega naught t. So therefore here I have already told you at omega naught t is equal to 0, its value is equal to 0. At omega naught is equal to pi, its value is 2 Vs. So this is the way it is going to get. So this is the graph we are going to get. After that it will be always constant, because a capacitor voltage cannot change instantaneously. So therefore its value will be always in this manner. So steady state voltage is just 2 Vs. So based on this we can say the diode voltage, and initially from 0 to omega naught t is equal to pi it will be 0, but after that it will be minus Vs. So from omega naught 0 to pi the VD voltage is it's conducting, so therefore its voltage is 0, but after that it is going to be reverse bias, so therefore its voltage is minus Vs. So therefore it is always from steady state. So this is the maximum voltage experienced by the diode. So therefore we can say the peak inverse voltage of the diode is equal to supply voltage itself. Now we are going to study the another case, which is diode LC circuit with initial condition. Suppose if initial condition is there, then if you are going to keep the diode, then what is the nature of the current, voltage across the capacitor, and the voltage across the inductor, and the diode voltage, everything we are going to see. So this is plus minus Vd of t, plus minus VL of t, plus minus Vc of t, and this is the current I of t, and this is Vs. This is supply voltage, and everything now we are going to see in a very detailed manner. So I have already told you here the current, if the current is a positive, then only it is going to get conduct. Otherwise, after that if the current is negative means this diode is going to get off. Now write the general expressions of the capacitor voltage, current in the circuit, and the voltage across the inductor, as you have already know, which is Vs into 1 minus cos omega naught t plus Vc. Plus here Vc naught means nothing but V naught we are going to assume, which is the initial voltage across the capacitor. So Vc naught into cos omega naught t, I of t is equal to C by L into Vs minus Vc naught into sin omega naught t, and VL of t is equal to L into di by dt is equal to Vs minus Vc naught into cos omega naught t, where omega naught is equal to 1 by under root over Lc. So now here this current can be only positive. The current can be only positive for up to omega naught t is equal to pi. After that it will be negative. So therefore this diode is going to conduct only from 0 to pi only. After that it is going to become negative, means the diode is going to become off. So therefore only all these equations are going to hold only for this range, which is 0 less than or equal to t less than or equal to pi by omega naught. Only for this region only all these equations are going to get hold. Now the peak inverse voltage of the diode is equal to, now it is going to become Vs minus V naught, or we can say V naught is called as the initial voltage across the capacitor. So therefore Vs minus V naught is the peak inverse voltage of the diode, and Vc naught is nothing but Vc naught or V naught. This capacitor voltage at t is equal to 0, I am going to assume, which is Vc naught or V naught, anything you can take, and always its value is always lesser than the supply voltage. So now I am going to draw the graphs of each and everything. So I of t expression is here under root over C by L into Vs minus V naught sin omega naught t. So you are going to get a sine wave only from 0 to pi only. After that it will be always 0. So therefore the maximum value is under root over C by L into Vs minus V naught. And whereas VL of t, the expression is nothing but here we are going to get Vs minus V naught into cos omega naught t. So therefore if you substitute omega naught t is equal to 0, we are going to get at omega t is equal to 0, we are going to get Vs minus V naught, and if you substitute omega t is equal to pi by 2, we are going to get 0, and omega naught t is equal to pi, we are going to get negative of this one, so minus of Vs minus V naught. So this is the way you are going to get for in this region. And similarly if you substitute omega naught t is equal to 0 here in the Vc of t, the expression which is Vs into 1 minus cos omega naught t plus Vc naught into cos omega naught t. So if you substitute omega naught t is equal to 0, we are going to get finally Vc naught or V naught. Suppose if you substitute omega t is equal to pi, we are going to get 2Vs minus V naught. So we are going to get 2Vs minus V naught. So after this, the current will be 0. As the current is equal to 0, then definitely inductor voltage will be always equal to 0. But capacitor voltage will not change instantaneously. So its value will be always same as the previous case, which is the 2Vs minus V naught. So you can see clearly the diode voltage is equal to supply voltage minus inductor voltage minus capacitor voltage. But the inductor voltage is 0. So therefore, the diode voltage is equal to supply voltage minus capacitor voltage. So Vs minus of 2Vs minus V naught. So we are going to get Vs minus 2Vs plus V naught. So therefore, we are going to get minus Vs plus V naught. So this is called as the peak inverse voltage. If you take minus common, so minus of Vs minus V naught. So this is the peak inverse voltage. We are going to get minus of Vs minus V naught. So this is the diode voltage we are going to get after the pi. So therefore, from here to pi, the diode is going to get conduct. So its value is always 0. But after that, it will be reverse bias, because Vs is always greater than V naught. So therefore, its value is positive, and positive to negative is always negative. So therefore, we can say it is going to experience a negative voltage. So it will be off. So simply we can say this is the call as the peak inverse voltage, the maximum voltage experienced by the, only we have to take the magnitude value. So the maximum voltage experienced by the diode in this case, which is Vs minus V naught. So now we are going to study the discharging LC circuit. Discharging means here we are not going to keep any DC source. Only with the initial capacitor voltage, it is going to discharge its energy into an inductor, and then we are going to see what is the nature of current and voltage of each and every element we are going to study. So let me assume this is the plus and this is the minus. So capacitor is going to deliver the current in this manner. So now see, this is called as a diode and this is a inductor. So this is plus or minus VL of t plus or minus VC of t. So before the switch is closed, I am going to assume the capacitor is going to have some special as voltage, initial voltage, which is, let me assume VC naught or Vs. It is equal to Vs, I am going to assume in this case. So therefore, let VC naught is equal to Vs, then Vc of t is equal to, see, if you substitute Vc naught is equal to Vs and the supply voltage is equal to 0, so finally you are going to get expression which is Vs into cos of omega naught t. And I of t we are going to get, see, there you are going to get negative, means if this current in this direction means negative, so in this direction means it is a positive. Therefore, you have to go for the positive side, which is Vs into under root over C by L into sin omega naught t. And peak inverse voltage, now we are going to see what is the peak inverse voltage experienced by this diode, which is Vs. So now we will discuss why it is going to get like this. So with this, so we know the value of capacitor voltage and the current in the inductor. So you can see clearly when the diode is on, both the voltages are always equal. So therefore, VL of t is equal to Vc of t. So the diode is on. Omega naught is equal to 1 by under root over LC. So you can see clearly here sign is positive only for 0 to pi. Only 0 to pi the current is positive. So therefore, if you draw this expression, means all these are going to hold only for omega t is going to lie between 0 to pi, or simply for 0 less than equal to t less than equal to pi by omega naught. All these equations are going to get on. So therefore, you are going to get here finally the maximum value is Vs into under root over C by L. So after that the current is 0, because current is negative means the diode is going to become off. Now inductor voltage, and inductor voltage is equal to capacitor voltage. So if you substitute omega naught is equal to 0, we are going to get Vs, and if you substitute omega naught is equal to pi by 2, we are going to get 0, and if you substitute omega naught is equal to pi, we are going to get minus Vs. So this is the graph we are going to get for the inductor. But when current is equal to 0, definitely we are going to get inductor voltage is also equal to 0. And the graph of VL of t and VC of t is same for both up to pi, both are same. But after that, capacitor voltage cannot change instantaneously, whereas the inductor voltage can change instantaneously. But this cannot change instantaneously, so it will be same as this one. So this will be equal to minus Vs. So now here, now I am going to write the KVL, which is in this loop at when it is off. When it is off, or simply we can say plus Vc of t minus Vd of t minus VL of t is equal to 0. So therefore, plus Vc of t minus Vd of t minus VL of t is equal to 0. At omega t greater than pi, then definitely VL of t is equal to 0. So therefore, Vc of t is equal to Vc of t is equal to Vd of t. So whatever the Vc should be equal to Vd. So with negative Vs means it is also negative Vs. So therefore, diode is reverse biased. So therefore, we can say that as the diode is reverse bias, the switch is open. So therefore, the peak inverse voltage experienced by the diode is Vs. So Vs is the peak inverse voltage experienced by the diode, where Vs is called as the initial voltage of the capacitor. So now we are going to discuss about the Fourier series. So any periodic signal you can write in terms of sine and cos, which is f is equal to a naught plus sigma n is equal to 1 to infinity an cos n theta plus bn sin n theta, where theta is equal to omega naught into t. So a naught is equal to 1 by 2 pi integration of 2 pi f of theta into d theta, or 1 by time period integration of time period f of t into dt. Similarly, an is equal to 2 by 2 pi integration of 2 pi f of theta into cos n theta d theta is equal to 2 by t integration of over the time period t f of t into cos n omega naught t into dt. Similarly, bn is equal to 2 by 2 by into integration of 2 pi f of theta into sin n theta into d theta is equal to 2 by capital T integration of over the time period t f of t into sin n omega naught t into dt. So this is with respect to theta and this is with respect to time period t. So you can go for any of these, you are going to get the same result. So f is equal to a naught plus sigma n is equal to 1 to infinity an cos n theta plus bn sin n theta, where a naught is equal to 1 by 2 pi integration of 2 pi f of theta into d theta is equal to 1 by capital T integration of time t f of t into dt. Similarly, an is equal to 2 by 2 pi into integration of 2 pi f of theta into cos n theta into d theta is equal to 2 by capital T integration of time period t f of t into cos n omega naught t into dt. Similarly, bn is equal to 2 pi integration of 2 pi f of theta into sin n theta into d theta is equal to 2 by capital T integration of time t f of t into sin n omega naught t into d theta. So this is with respect to theta and this is with respect to time period t. So you can go for any of these, you are going to get the same result. See, if f of t is an even function, f of t is an even function means it is symmetric with respect to y-axis. So f of t is equal to f of minus t, then we are going to say that this function is said to be an even function. Then a naught is not equal to 0 and an is not equal to 0, whereas bn is equal to 0, because if function is the even, this is not 0, this is not 0, but even into odd is again odd. So integration over one time period of odd signal is always going to give you 0. Similarly, if f of t is odd signal means f of t is equal to minus of f of minus t, means it is antisymmetric with respect to y-axis, then we are going to call this function as said to be an odd signal. So for odd signal, always f of 0 is equal to 0. So therefore, for odd signal, a naught and an is equal to 0, whereas for bn, odd into odd is again even. So therefore, here we are going to get not equal to 0. So only bn is not equal to 0, whereas a naught and an is equal to 0. Because integration of odd signal is equal to 0, odd into even is again odd signal. So integration of odd signal is also going to give you 0, but not bn. F of t is equal to a naught plus sigma n is equal to 1 to infinity jn cos nt plus bn sin nt is equal to a naught plus sigma n is equal to 1 to infinity cn sin of nt plus theta n. So you can write in this fashion also, where a naught is equal to 1 by t integration of 0 to t f of t dt, where n is equal to 2 by t integration of 0 to t f of t into cos nt dt, whereas bn is equal to 2 by t integration of 0 to t f of t into sin nt dt. The t is called as a dummy variable, whereas cn is equal to under root over an square plus bn square, whereas theta n is equal to tan inverse of an by bn. So this is the general format, which is f of t is equal to a naught plus sigma n is equal to 1 to infinity an cos nt plus bn sin nt is equal to a naught plus sigma n is equal to 1 to infinity cn sin of nt plus theta n, whereas cn is equal to under root over an square plus bn square and theta n is equal to tan inverse of an by bn, whereas a naught is equal to 1 by t integration of one time period f of t into dt, and an is equal to 2 by t integration of one time period f of t into cos nt dt, whereas bn is equal to 2 by t integration of one time period into f of t into sin nt dt, where t is called as the dummy variable. So this is the way you can figure out the coefficients of the Fourier series. A small example, you say this is called as an odd function. So this is like this odd function with respect to y-axis. So v0 is an odd function. So this is the odd function, some example output signal. Then for an odd function, I already told you a naught is equal to 0 and an is equal to 0, whereas bn is not equal to 0. So now I want to find what is the value of the bn. So bn, the general formula of bn is equal to 2 by 2 pi integration over 0 to t f of theta into sin n theta into d theta. So I'm going to split into two parts. So this 2 pi I'm going to split into two parts, 0 to pi and pi to 2 pi. So 0 to pi, which is Vm. So you are going to get V into sin n omega naught t into d theta, or simply sin n theta into d theta, plus pi to 2 pi minus V sin n theta into d theta. So therefore, if you do the integration, we are going to get, see V is a common, I'm going to take it outside, and 2 cancels, we are going to get V by pi. See, integration of sin n theta. Integration of sin n theta is minus cos n theta by n. Substitute the limit 0 to pi, plus, and integration of minus sin n theta. So minus sign is nothing but cos. So cos n theta by n. Substitute the limits pi to 2 pi. So V by, see now n is a common, I am going to take it outside. So if you substitute the upper limit minus lower limit, so you are going to get finally in this format. So here this is a 1. So cos 2n pi. Cos 2n pi is nothing but, so cos 2n pi is always equal to 1. Cos 2n pi is always equal to 1, because no matter whatever the n, it is always equal to even function. So even function is nothing but, we are going to get always 1. So 1 plus 1 is 2. Similarly here minus cos n pi minus cos n pi. So minus 2 cos n pi. So finally you are going to get 2 minus cos n pi. So if you take 2 outside, 2 by n pi into 1 minus cos n pi we are going to get. So this is the coefficient of the Bn. So when n is equal to even, what is going to happen? When n is equal to even cos n pi is equal to. So when n is equal to even, cos n pi, see cos 0 pi is equal to 1 and cos 2 pi is equal to 1. So like that it is going to become 1. So 1 minus 1 is 0. So therefore Bn is equal to 0. When n is equal to odd, cos n pi is equal to. So cos n pi is equal to, when n is equal to odd, so n is equal to 1, we are going to get minus 1. So like that. So if you get minus 1, you are going to get 4v by n pi. So simply we can say cos n pi is equal to minus 1 over the power of n. When n is equal to r, it is equal to minus 1. When n is equal to even, we are going to get plus 1. So cos n pi is equal to minus 1 over the power of n. So cos n pi is equal to minus 1 over the power of n. So simply we can say cos n pi is equal to minus 1 over the power of n. So we can say that for n is equal to even, definitely Bn is equal to 0. When n is equal to odd, we are going to get Bn is equal to 4v by n pi. So V naught is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin n omega naught t. So this is the expression of that output signal, that is our signal. So therefore V naught is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin n omega naught t, where V is the peak value of that signal. So therefore V naught is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin n omega naught t. So 4v by n pi into sin n omega naught t. So V naught is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin n omega naught t. Suppose I am going to shift that signal. If I shift that signal some by a small amount of alpha, that new signal is called as the x. So this is the new signal which is obtained by shifting the previous signal by a small amount of angle alpha. Then you are going to get the new signal expression, which is x is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin of n omega naught t minus n alpha. So this is the new, you can say new signal expression, which is x is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin of n omega naught t minus n alpha. So alpha is the amount of it was shifted. So this is the new signal x of t. So x is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin of n omega naught t minus n alpha. For this signal, V naught is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin n omega naught t. Whereas for this signal, x is equal to sigma n is equal to 135 up to infinity 4v by n pi into sin of n omega naught t minus n alpha. So now we'll discuss about the rectifier and its classifications. So rectifier and its classifications. Suppose there is an uncontrolled rectifier. Uncontrolled rectifier means it is going to use only the diode, because uncontrolled means the circuit on and off, the device on and off is depend only on the circuit itself. So because of that it is called as uncontrolled rectifier. It is going to use the diodes. So if you give a fixed AC, we are going to get a fixed AC. So with the help of uncontrolled rectifier, if you give a fixed AC, you are going to get output as a fixed DC. So basically rectifier is going to convert AC to DC. But if you use a fully controlled rectifier, means every switches are the thyristors. Fully controlled means each and every switch inside that is a thyristors. Thyristors are called as the, see these are the fully controlled rectifiers, means they are going to basically use the everything as a thyristors. Then we can say if you give a fixed AC, if you give a fixed AC as the input, then output we are going to get a variable DC. So therefore here we can do the operation of controlling the on of the thyristor depending on our value. So therefore we can control the DC output voltage. For a fixed AC, we can get a variable DC. So fully controlled rectifier means each and every device in that is a purely thyristor. So because of that only we say it is a fully controlled rectifier. So therefore here all position is under our control. So therefore we are going to get a variable DC. Or we can also call it as a full converter. Whereas semiconductor means it is going to use some of the diodes and some as thyristors. See, semiconductor means it is going to use some as diodes and some as thyristors. Then also we are going to get a variable DC. So this input is a fixed AC means we are going to get variable DC. So for uncontrolled rectifier, if the input is fixed AC, we are going to get a fixed DC. If the device is a full converter, then we are going to get, if the input is fixed AC, we are going to get a variable DC. If the circuit is a semi-converter, if the input is fixed AC, then also we are going to get a variable DC. So generally we are going to assume that there are no losses in the switching. We are going to assume that there are no losses in the switches. So therefore whatever the input power should be equal to output power. So input power is a Vs Is cos phi is equal to P output power. So Vs Is cos phi is called as the Vs means RMS value of the input voltage, Is means RMS value of the input current, and cos phi is called as the power factor of the input. So under ideal condition we are going to assume that all the switches are not going to consume any power. So therefore whatever the input power should be equal to output power. So Vs Is cos phi is equal to output power. Vs is called as RMS value of the input voltage, Is is called as RMS value of the input current, and cos phi is called as the power factor of the input. So now we are going to study about the pulse number. Suppose if the output signal having only one pulse, see only one pulse is there, and 0 to pi there is some wave, but after that there is a 0. So this is called as a one pulse, means only output has one pulse. So this is called as a ripple voltage. The peak to peak value is called as a ripple voltage. So this is the one pulse converter, or simply we can say it is the output of a single phase off wave converter waveform. This is the output of a single phase off wave converter waveform. So one pulse is also called as one pulse converter or single phase off wave converter waveform. Suppose if you are going to get two pulses from 0 to pi one pulse and pi to 2 pi it is another pulse. So therefore in a given period of 2 pi we are going to get two pulse. So it is called as a two pulse converter, and this is called as a peak to peak voltage is called as a ripple voltage, and this we are going to call it as this is the output of a single phase full wave converter waveform. This is the output of a single phase full wave converter waveform. See, 3 pulse converter means in a given period of 2 pi we are going to get 3 pulses, then it is called as a 3 pulse converter, and this we are going to call it as the ripple voltage. And simply we can say that this is the output of a 3 phase off wave converter waveform. 3 phase off wave converter waveform. Suppose 6 pulse converter means in the output we are going to get 6 pulses in a given period of 2 pi, then we are going to call this as the 6 pulse converter, and this is called as the ripple voltage. So this is the output of a 3 phase full wave converter waveform. So this is the output of a 3 phase full wave converter waveform. See, one pulse converter is the output of a single phase off wave converter waveform, whereas 2 pulse converter is the output of a single phase full wave converter waveform, whereas 3 pulse converter is the waveform of a 3 phase off wave converter waveform, whereas 6 pulses is the output of a 3 phase full wave converter waveform. So this is single phase off wave converter waveform output, single phase full wave converter waveform output. This is 3 phase off wave converter waveform output, and this is 3 phase full wave converter waveform output. So 1 pulse, 2 pulse, 3 pulse and 6 pulse. So 1 pulse is the output of a single phase off wave converter waveform, 2 pulse is the output of a single phase full wave converter waveform, and 3 pulse is the output of a 3 phase off wave converter waveform, and 6 pulse is the output of a 3 phase full wave converter waveform. So suppose now we are going to find what is the RMS value of the signals. Suppose there is a current like this. Here only for 0 to t on the current is going to have some value of I0, and the remaining period the current is equal to 0. Then what is the RMS value of the signal? RMS value of the signal is equal to I0 into under root over t on by t. So this is called the RMS value, but average value is equal to I0 into t on by capital T. Whereas suppose that the other signal of this format, which is from 0 c, is going to have same pulse width of x and x, then I want to find what is the RMS value and the average value of this signal. So RMS value of this signal is equal to here I0 into under root over 2x by t, and I average is equal to, I am going to get 0 because this is positive and this is negative. So overall value we are going to get 0. But IRMS is equal to here I0 into under root over 2x by capital T. So now we are going to study one more important concepts like input, power semiconductor devices, output and converter names. See, if the input is AC, if the input is AC and if the power semiconductor devices which are used are diode and thyristors, and if the output is DC, then we are going to call it as the uncontrolled rectifier or the controlled rectifier. Now we are going to study if the input, see, based on the input and the power semiconductor device used and the output and the converter's names. If the input is AC and the power semiconductor devices which are used are diode and thyristors, and if the output is DC, we are going to call it as the uncontrolled rectifier or controlled rectifier. If you are going to use pure diode, it is called as the uncontrolled rectifier, and if you are going to use the thyristors, then it is called as a controlled rectifier. If the input is AC and if you are going to use the thyristors and if the output is still AC, we are going to call this as the AC regulator or AC voltage controller. So AC to AC is called as a AC voltage controller. And AC to DC is called as the control rectifier. It is a rectifier and this is a voltage controller. And AC to AC, if you are going to use thyristors, it is also called as a cycloconverter. So this is called as the cycloconverters. It is also called as a cycloconverters. If DC to DC, if you are going to use transistors, GTO and force converted thyristors, then we are going to call it as the chopper. Chopper means DC to DC conversion. If you are going to convert DC to AC with the help of transistors, force converted thyristors, then it is called as the inverter. See, if you want to convert AC to DC with the help of diode or thyristors, is called as the uncontrolled rectifier or control rectifier. If you want to convert AC to AC with the help of thyristors, it is called as either AC regulator or AC voltage controller or cycloconverter. So if you want to convert DC to DC with the help of transistors, GTO or forced converted thyristors, it is called as the chopper. And whereas if you want to convert DC to AC with the help of transistors, forced converted thyristors, it is called as the inverter. So basically rectifier means AC to DC conversion, and whereas cycloconverter means it is a AC to AC conversion, and choppers means DC to DC conversion, and inverters means DC to AC conversion. So rectifier means AC to DC, cycloconverter or AC voltage controller means AC to AC, and DC to DC is called as a chopper, and DC to AC is called as an inverter. In this class we have learned some of the basic concepts of the power electronics in a very well detailed manner. So if you like the content of our channel, then please to like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct message comes to mobile. If any improvements needed in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching the lecture. Keep smiling, take care and bye bye.